Good morning, Dr. Anant Govindarajan, sir.
Good morning.
Sir, can you please check your PPT? We made you as
Yes.
presenter, sir.
Okay, thank you. Let me just share my screen. Are you able to see my screen? The
Yes,
presenter.
sir. Yes, sir. Yes, sir. We can see.
Okay, and is the laser pointer also visible?
Yes, sir. It is visible, sir. Your
Okay.
audio is very clear, sir.
Okay, thank you very much.
Yeah. Sir, we'll
Should
wait
I
for a couple of minutes, sir, so that the participants
okay.
will join.
Should I stop sharing for now or
You can keep the title slide, sir.
okay, okay. I'll turn my video on. Uh,
If you are comfortable, you can keep your video on, sir.
okay, I'll turn it. I don't know how to turn it on now. One second. Yeah, now it's turned on.
Yeah, fine, sir. The participant strength is very less, sir, so we'll wait for a couple of minutes.
Yeah, sure. We can wait for some time.
Yeah.
Not a problem.
Sir?
Yeah, I'm here.
Yeah. So we'll start the session, sir.
Okay.
Very good morning to one and all who are present here, and warm welcome to you all for the fourth day's first session of 5-day virtual Atal FDP being conducted at MVJ College of Engineering, Bangalore. On behalf of the coordinating team, I welcome this session speaker and all other faculty participants for this 10th session of FDP. It gives me immense pleasure in introducing the speaker of current session, Dr. Anant Govindarajan from Indian Institute of Science, Bangalore. Dr. Anant is currently working as an assistant professor in the Department of Chemical Engineering, Indian Institute of Science, Bangalore. He obtained his BTech in Chemical Engineering from Indian Institute of Technology, Delhi in 2013 and MS in Chemical Engineering Practice from Massachusetts Institute of Technology, USA in 2015. He earned his PhD in Chemical Engineering from Massachusetts Institute of Technology, USA in 2019. He is a recipient of Carbon Nano Materials Graduate Student Award from American Institute of Chemical Engineers in 2018 and MIT Graduate Student Council Travel Award in 2018, Rosemary J. Award from MIT School of Chemical Engineering Practice in 2015, and Institute Silver Medal from IIT Delhi in 2013. His research interest includes multi-scale simulation of applications in nanotechnology, water desalination, energy storage, catalysis, using molecular dynamics, kinetic Monte Carlo, and density functional theory, and also includes development of kinetic and mechanistic models for chemical vapor deposition and predicting the shapes of nanospores and defects in the 2D materials. And his further interests include electrocatalysis for the sustainable energy conversion at 2D metals interfaces, and also the development of force field models for materials for combining ab initio simulation and experimental data. He has published many articles in international journals with high impact factor. So now in this session, Dr. Anant Govindarajan is going to share his views on the topic titled Introduction to Boosting Algorithms in Machine Learning. So with this brief introduction, I request Professor Anant to take over the session and enlighten our understanding with his expertise in the field of machine learning. Thank you all. Sir, over to you, sir.
Thank you very much, Professor Ramakrishna, for your very kind introduction. I'm very happy to be here, and I'm thankful to you and all the organizers for inviting me. And it is a pleasure to speak before all of you. I hope my screen is visible and you can see you can hear my audio.
Yes, everything is perfect, sir. So you can.
Okay. Thank you so much. So, yeah, as Professor Ramakrishna mentioned, the title of my talk is Introduction to Boosting Algorithms in Machine Learning. And hopefully, by the end of the talk, you will come to know what boosting algorithms mean and why they are gaining so much popularity in machine learning. Right? So, one of the structures that is shown here on the first slide, this is called a decision tree. So, now I'm not sure how many of you have seen this before. But this is a very common structure in machine learning these days, and it is very useful in kind of fitting a very complicated data set, right? And the ultimate goal is to somehow use this decision tree, and I'll explain how, to make some predictions of data, right? So if you have some actual data, it may be anything. In a chemical plant, you may want to predict what is the yield, what is the selectivity, what is the temperature of a reactor, right? So that's the measured data. And here you have the predicted data. And our idea is that those two should match. And when will they match? When the data points lie as close as possible to this y equal to x line, right? And that's what these points are showing, right? If you are able to get a machine learning model like this, that means you have done a very good job, right? And your model can predict the data in very well agreement, in good agreement with the actual data, right? So that is our goal for the talk today, to learn how these so-called boosting algorithms can help us reach this picture where we can combine our knowledge of machine learning to make a lot of predictions about data. So I'll start from the very basics. right? And try to convey all the concepts. If you have any questions, then please feel free to uh, raise your hand. I mean, I may not be able to see your hand, so you can also maybe someone could moderate, or if you want, you can directly go ahead and ask.
I'll do
Um,
it first, sir.
Okay, thank you.
Yeah, yeah.
So the first question I want to start with is machine learning. Of course, this is now the fourth day of the or the third day of the program, the faculty development program. So by now you of course know what is machine learning, but still I wanted to start from the basics so that this gives you a complete picture of what is happening. Right. So the main goal of machine learning is to instill in computers the ability to make predictions based on existing data, right? So what this means is you have a complicated data set and you want to teach the computer to understand this data set and also to make predictions in the future based on this, right? And there are many ways of doing this. And as I told you on the previous slide, our ultimate goal is to obtain a good match between the predicted and the actual data, and to obtain as less as possible of an error in these predictions. And if you look at this historically, so machine learning originated as an extension of statistics and, of course, control theory, which as chemical engineers we are very familiar with. We know what is controls. There's PID controllers, which try to maintain some level set in terms of, say, the pressure or the temperature. So you can understand why the concept of machine learning first came into the purview of people working in statistics because they deal with data, and people working with controls because they have to make some kind of decisions, right? They have to teach the computer to make some kind of decisions. So it's logical that machine learning began in those fields, but over the years, over the past 2 or 3 decades, this has really blossomed into a tool which all of us can use and can gain insights from, right? So what all is involved in a machine learning model? So to simply put, machine learning, first and foremost, it involves the estimation of learnable parameters or weights for regression models, right? And regression is a term that all of you would have heard quite frequently. You have linear regression, non-linear regression, multivariate regression, so many different types of it. And at the end of the day, machine learning is regression in one way or the other, right? You are training a model and you need some parameters of the model and you're trying to fit some data, right? And that's why we have to estimate these parameters and in a reliable manner, right? We don't want to overfit the data, right? We don't want to underfit the data. We want it to be just right so that the computer knows what the data set is about and how to make predictions using it, right? And the way to do this is to use something known as a gradient descent method. So that's an optimization technique which will help you optimize uh, the error between the predicted and the actual data, and ultimately you will get this kind of say a good match, right? So this gradient descent method is of course the most commonly used, most commonly taught method, but I mean there are other newer techniques which are often better than this. But I mean in an introductory sense, this gradient descent method is the most popular one in training machine learning models. Now, why exactly are we doing all this is because, I mean, in chemical engineering and even other branches of science and engineering, we are taught to develop models, right? And mostly these are physics-based models in the sense that you know what is happening, you are able to write down some equations. For fluid flow, it may be Navier-Stokes. For thermodynamics, it may be the first and second laws. Or if you're doing heat or mass transfer, you may have some correlations. But at the end of the day, it is all coming from the physics of the problem, right? But in many cases the physics is so complicated, there are so many processes happening that it is not possible to derive closed form expressions, right? Especially when your data is high dimensional. And by high dimensional I mean that there are so many independent variables. Take just the example of a reactor, right? In a chemical plant you will have the temperature, you will have pressure, you will have the feed composition, right? You will have the residence time, you will have the residence time distribution in the reactor, right? And you will have the volume of the reactor and the head space. There are so many different things which come in, and at one point the variables are so many that you cannot derive a closed form expression. And this is where ML comes in and it mitigates these issues related to the lack of closed form expressions and to the presence of very hyperdimensional or high dimensional data, right? So if you look at a single point in this plot, right, the plot between predicted data and actual data, a lot of work has gone into making this prediction. And let's see what is actually that information. So let's take this point. So what could actually happen is there could be many features, right, based on which this prediction is made. And I'm just giving numbers and symbols here, x1, x2. There could be like 50 features, 100 features, we don't know. And that is what I mean when I say the data is high dimensional. There are many features, and all of them may be important in predicting your data. And the only way to know is to kind of exclude some features and see whether the model still works or the model breaks down. Right. So I hope it is clear what exactly is machine learning and what we are trying to do here. Now, I'd like to categorize the machine learning algorithms into different types. And this is kind of useful because for particular applications, certain algorithms are better. For other applications, some other ways of making predictions may be better, right? So this is machine learning. And the first type of machine learning is called supervised learning. And what we do here is that we train a model based on targets, right? So we have certain targets which we want to predict. For example, in a chemical plant, we may want to predict the conversion or yield, as I said, or we may want to predict what is the outlet feed composition, right? And what we do is we have a lot of historical data, and then based on that data we tell the computer, okay, when the conditions were like this was the yield. During other conditions, something else was the yield. And you kind of supervise the computer as it learns the data set, right? So that's what is meant by supervised learning, and it applies to both regression and classification tasks. Now we'll come on to the next slide, and then we'll explain what is meant by regression and classification. But I'm assuming that some of you may already know what these things mean, if not all of you. And the difference with unsupervised learning is that here the targets aren't specified. So you sort of let the computer deal with the data itself and learn the underlying structure of the features based on some metric of similarity, right? So you ask the computer to kind of learn what are the different features and what's going on in terms of the model being different, right? So let's look at this data set here. On the bottom left, there are two features in this model, just for example. So feature one, which is on the x-axis, and feature two, which is on this vertical y-axis, right? And there are three sorts of, you can see regions. I've marked with blue, orange, and red color here. And what is happening is that to your eye, you can of course see that these are different, okay? Now in supervised learning, you would tell the computer that they are different, right? And then given a new point, you want the computer to tell which of the three regions it belongs to, right? On the other hand, in unsupervised learning, you want the computer by itself to understand that there are three different regions. And then any other new point which comes, again, the machine learning algorithm can tell you, okay, this is the region it belongs to. So a famous class of algorithms in the unsupervised learning is called clustering, right? And why it's called clustering? Because it will basically divide your data set into different clusters which are related to each other. And that is exactly what we are doing here, right? When we talk about these different regions, these are essentially clusters of data points, and it's a challenge how to treat or how to teach the computer to identify clusters in your data set. Now, the main question, of course, is do you want to tell the computer that the three groups on the left are different, or would you like the computer to figure it out itself? If you tell the computer, that's supervised learning, so that the computer learns under your supervision. And if you let the computer figure it out itself, then that means it is unsupervised learning, and the computer is kind of learning on itself, right? So I hope this categorization of ML algorithm gives you some idea of what is going on in terms of the different classes of algorithms that are available and the different classes of machine learning that are available. Now let's go a little bit deeper and try to understand these regression and classification tasks, right? So we'll give first some examples of supervised learning. For example, someone gives you this structure, right? So this is there's a benzene ring and then this carboxylic acid and again some kind of OO group here. So the question is this molecule soluble in water or not, right? And you may have like a big data set. Say you have like thousands of molecules and you know whether they're soluble or not, or maybe better, you know their exact solubility, and then you teach the computer that these are the structure, this is the solubility. Now based on that supervised learning, if you are given a new structure, right, can you predict if it's soluble in water? So that's a classic example of a problem in supervised learning, right? Another example could be that let's say you're interested in a nanopore in a material, right? And then you're given the structure, and you see at the edge there are different types of atoms in a lattice. So these are called zigzag atoms. These are called armchair atoms, and these are singly bonded atoms, right? You can see this forms a zigzag wavy structure. This forms like a chair like armchair structure, right? So these are different types of atoms, and what you are telling the computer is, look, this is the photo of the pore. Can you tell me how many armchair or zigzag atoms are there in this nanopore? And again, the way to do it is you need to have tons and tons of data. Maybe you have 10,000 pores or something like that, and then you teach the computer like for each pore how many types of how many different atoms are there. And then if you give a new pore to the algorithm, then it will tell you the number of armchair and zigzag atoms that are present in it. Okay, so that's another example of a supervised learning. And then another example, which is kind of related to the current scenario is, let's say you are given the X-ray of someone's lungs, and then you want to predict if they are suffering from COVID or not. And this is again through some kind of machine learning and image-based algorithms. Basically, if you have like a database of X-ray images, and then the computer kind of figures out. But recently, there's also there's caveats everywhere, right? So what happened in one study was that there are labels in X-rays, right? Sometimes the name of the hospital is written. Sometimes you have information like kilovolt and what was the voltage at which all these things were done. So what was happening is the computer, instead of only learning the X-ray, it was learning the information written here. And then it thought, so there are some hospitals which had more COVID cases, and then it thought that only those hospital could have COVID cases, the others could not have. So you see, the computer is only as intelligent as you make it to be, and there can be mistakes like this which can happen. And that is why you, as the developer of the model, you have to be the person who decides like what is going to happen and how you're going to make the model learn the actual features and not something spurious which may actually lead to wrong predictions made by the machine learning algorithm. Okay, so I hope this kind of gives you a brief overview of three different examples of supervised learning, and one from more like chemistry and chemical engineering, one from say material science, and one from medical diagnostics. So obviously, I mean, machine learning can be applied to any different field, and if you're working in any other field as well, you can think of examples of supervised learning which come from that field, right? So the main take home message here is that in each case, you will have to train the computer with some amount of data, and only then it can make a prediction, right? So let's move on to some examples of unsupervised learning, right? So what happens here is that the computer, of course, recognizes, right, the structure in the data itself. And one famous example of this is, say, recommendations on Netflix or Amazon Prime, right? These days, a lot of us are consuming content on these kind of platforms, and then based on your viewing history, Netflix may make some recommendations. And the thing is, your viewing history changes with time, right? So maybe yesterday you were, or maybe 2 years ago, you were more interested in, say, Kannada movies, but now you're more interested in English movies, right? So your viewing preferences change with time, and it's difficult to kind of have a supervised machine learning here. So this is where the utility of unsupervised learning comes into the picture. So the computer can learn itself, and it can tell you, okay, this person is now interested in watching Hindi movies, and he's the one. These are the suggestions that will be given to him. or her, right? So that's the kind of machine learning which is going on behind the back. And also the categorization of news into buckets, right? So if you open Google News, you will see that there's so many different categories like Indian news, world news, business news, technology news. So how does, when a news article is published on a news website, how does Google know that is this Indian news, is this business news, is this technology, right? So this is some kind of machine learning. Of course, there's no person sitting behind and tells for each article, right? There's way too many articles to be doing that. There's every day hundreds of thousands of articles are being published, and it's no way possible for a human being to sit and tell Google, okay, this is what the article is about. So it's some kind of unsupervised learning, clustering, which is happening when the computer is able to figure out, okay, this article is something related to entertainment, or this article is related to sports. And this is again a very common example of unsupervised learning, right? And again, the main message is that in each of these cases, you would like the computer to figure out the structures of the features itself. And that's why we are interested in these kinds of algorithms, right? Of course, in this talk, I'm mostly going to be focused on supervised learning because that is, I feel, more relevant to us as chemical engineers. We have some data sets, and based on that data sets, we want to make some new predictions. And there, of course, supervision is important and helpful in training the appropriate machine learning model. All right. Now, there are two main types of supervised learning. And these, as I already mentioned, one is called a regression learning. And this is used to predict a continuous variable. And one example could be, given data in a plant, what is the temperature of a reactor? And this is something I already alluded to, right? And another example could be, another type of learning is classification learning. And this is used to classify data into a fixed number of categories. So the number of categories in which you are classifying or binning the data could be either two or more than that, right? When you classify into two types, then it is called binary classification. When you classify it into many types, then it is called multi-class classification. And this uses a technique known as logistic regression, right? And one example of binary classification is this, right? So instead of asking this quantitative data, which is given the plant data, what is the temperature of the reactor, I'm asking a more qualitative question. Given the plant data, has the reactor overheated or not, right? And the answer to this is yes or no, right? So there's only two classes. Either the reactor has overheated or it has not. So this means this is an example of a binary classification problem. And of course, you can also have multi-class classification problems. Now, this is an illustration, right? So there are two types of questions, as I said. If you want to predict T, which is a continuous variable, then this is going to be a regression problem. Then if you only want to predict some qualitative question like whether the reactor has overheated or not, then it is going to be classification learning here. Now, I give you another example, which is not quite related to chemical engineering, but I mean, in the machine learning community, of course, it is well recognized. So given this photo, right, there are two questions you can ask. One is it a cat or a dog? And the second is, from the photo, let's say you want to predict what is the age of the animal, right? So hopefully you are able to figure out which of these two questions can be answered by regression learning and which of these two questions can be answered by classification learning, right? So that's a classic problem in machine learning. Are there any questions at this point?
No, sir. So far, participants, do
Okay.
you have any questions? So you can use the chat box to ask your question, or you can unmute yourself and ask the question.
Okay. So I'll go ahead and yeah, the audience should feel free to ask questions. Okay. So now that we have done this, we of course need to come up with some metrics to classify, to model correctness. Okay, there's a question. Could you please read the question, Doctor? I cannot see it somehow.
Yes, sir. Can you please differentiate ML, AI, and ANN?
Right. So ML is, of course, what we have discussed so far, right? What we are trying to develop models to make some predictions. So that is machine learning. Now, AI is something little bit beyond ML, right? You don't just want to predict data, you want to teach the computer to make decisions. Let's say you have self-driving cars, or you have robots, right, doing some manufacturing or synthesis. So that is more like artificial intelligence, because you are mimicking human actions with that computer, right? So ML is more restricted. It's more like teaching a computer or making it learn about this data. AI is making it more intelligent like a human being, which can do actions, robotics, self-driving cars, and so on. And then artificial neural network is just a class of machine learning called deep learning, where basically you use something called neural networks to represent the data. So in this talk, we'll focus on decision trees, right? That is one class of supervised learning. But artificial neural network is another class of supervised learning where you mimic the structure of a brain, right, in terms of a neurons. So there are many neurons, and then based on the input to those neurons, you will get some output, right? So it's just one class of supervised machine learning. I hope this answers your question. Right. So if there are no further questions, then we'll move on to the next topic, which is metrics to quantify the correctness of models. And this is done through something known as an objective or a loss function, right? And this tells you how close the predicted data is to the experimental or measured data. Now, it can be done using many, many different metrics. I'm only listing three of them here. The first one is called mean squared loss or mean squared error, or it's also called quadratic or L2 loss. And this is something you may have seen before, right? If there are n data points and y hat is the predicted data and y is the actual, say, simulated or experimental data, then you just take the difference, you square it, and then you do 1 by n, right? And why people prefer it is it's easier to compute the gradients here, right? And that's why it's very often used. And sometimes instead of the mean squared error, you can have the mean squared percentage or relative error. So if you just divide inside the bracket by the actual data, then you can get the percentage deviation. And using the percentage deviation sometimes is quite useful, especially when your data is spanning a wide range, right? So sometimes you can see that only the higher data points will get predicted correctly. That's because their absolute error is higher. So if you want both the lower and the higher data sets or points to be predicted correctly, then you can use the relative error to mitigate this problem. There's also another type of error called mean absolute error, or L1 loss. And this one is simply defined in terms of the absolute value, right? You take the absolute value of the deviation of the predicted and the measured data, and then you average it over n samples. And this L1 loss is more robust to outliers, right? Because the problem here is you are squaring. So if something is very far off, that quantity is going to blow up, right? So whereas that will not happen here, and that's why this L1 loss is more robust to outliers, since the square term is not involved. However, I mean, derivatives are slightly more cumbersome. As you know, this function is also not discontinuous. It is not differentiable when the error is zero, right? You have a V-like shape when the error is zero. So there are some limitations associated with this function. And the third type of function I want to introduce is this mean squared logarithmic error. In case you have normally distributed data, you can use this. And you see that there's this +1 here, and that's just because, let's say, you cannot have log of 0, right? It's not defined. So how you mitigate that is you add +1. And the other thing is that your y cannot be too negative, because again, log of negative numbers are not well defined. You'll go into some complex numbers. So it's better to use it only for positive data, or even like non-negative data, right? Even if you have 0, you can add +1 and get away with the problem here. So these are three different kinds of loss functions that can be used to calculate how good your model is as compared to the measured or the predicted data from simulations or experiments. And of course, another metric to quantify how good a model is the R square metric. You would have seen at many places that R squared is in some sense also related to this mean squared error. And if you pick up any statistics textbook, it'll tell you what exactly is the R squared prediction and why it must be close to 1 if you want to have a good model. Now, once you have the loss functions, how do you kind of optimize a machine learning model? And let's start with the simplest possible supervised regression model, which is a linear model. And what you are seeing here is that based on some feature, you have a plot of the data, and this more or less looks like linear. So the question is, what is the slope and what is the intercept of this straight line which can fit all this data, right? And here I'm only showing against one data, but really you can have, as I said, 50 features, 100 features, and then it may be linear in all of these features, and you want to find the best possible slope of each feature, and then of course the intercept which adds to all of that, right? So the model is linear in features. So then you can write it in this form, right? So y hat is the prediction. So that's f of x, and x are the features. And because there are multiple features, you kind of have to sum over all the features. So I is the number of data points, right? So you can have 10, 20, 30 data points to fit. And then these j are the parameters. So in this model, there are p plus 1 parameters. Why p plus 1? Because you have p slopes. So these betas are the slopes. And then this b naught is actually the intercept, right? So you have p plus 1 parameters. And you can write this in terms of a matrix representation, right? So y hat, this capital Y is a matrix, is x beta, or y hat is actually a vector. X is a matrix, and then this beta is also a vector, right? And the mean squared error, which is also called the residual sum of squares, can be calculated just in the following way, right? So you take y minus x beta, that's the error. And of course, you want a single metric. So you're doing y minus x beta transpose y minus x beta. That gives you one value for the mean squared error as a function of beta. Now, this is a quadratic function in the p plus 1 parameters, and this should be minimized with respect to beta if you want to get the right value of beta. And that's what we're going to do. We differentiate this with respect to beta, and then we get the derivative, which is minus 2 x transpose y minus x beta. And of course, we also have to check the second order derivative, right? It should always be positive if you have a minimum. And of course, if you have a matrix, then it has to be positive definite, right? When you have matrices, they're no longer positive or negative. You have to check whether they are positive definite or not, and that's more related to the eigenvalues of the matrix. Now, if you set this derivative, this term here to 0, let's see what you'll get. You'll get x transpose x beta should be equal to xy. And since our goal uh, is to obtain beta, you can just multiply both sides by the inverse of x transpose x, right? And that's what we did here. So then the optimal value of beta is x transpose x inverse, the whole multiplied by x transpose y. And x is the matrix of data points, and y is the column vector containing all the data, right? So this is the optimal set of parameters for the linear model. But the question is, right, not always the model is linear. We may want to have some kind of a non-linear model. And then how do we obtain the model parameters in such a case? And this is where the concept of the gradient descent algorithm that I had introduced before, that is going to come into the picture. So let's talk about the gradient descent method. And what you're actually doing here is that you have the loss function, and let's say this is the contours, right? There are different parameters, x0, x1, x2, right? And this is essentially related to the parameter. So it's actually beta naught, beta 1, beta 2. And you want to go to the minimum here, right? And at each point, each iteration, you're trying to proceed more and more towards the minimum. And in mathematical forms, if L is the loss function, then the new set of parameters, beta n plus 1, is just beta n minus gamma times the gradient of L. And this is why this method is called gradient descent, because it involves the gradient of the loss function at the previous set of parameters, and then you add this to the beta n to get the new set of parameters, right? So what is this gamma? So this gamma is called the learning rate, and it is actually a very important parameter. N is, of course, the iteration number. You may have to do 100 iterations, 200, we don't know. We'll have to figure out when the error is small enough for you to stop. And this nabla gradient of L is basically the gradient of the loss function. Now, the descent is stopped when the mean squared error or any loss function is lower than a threshold. And the question is, what is the learning rate that you use? So we have to fix an optimal learning rate. So too low a learning rate, what will happen? you will need many iterations, maybe 1,000, 2,000, or maybe you won't converge at all. It will just be so slow. And the second one is too high a rate, it will cause overshooting, right? Because let's say you're starting here and you took a very big step, you can reach here, right? So maybe you will reach here. Next time you take a big step, you again come back here. So it's kind of oscillating about the minimum, and you are never able to reach the minimum. So of course, the learning rate can be too slow, right? You go very slowly here, or it can be too fast, it just oscillates here. So that's the problem, and you want to avoid that problem here, right? So what do we mean when we say the model is learning? This is what we mean, right? Basically, this straight line is the best fit to this y versus x data. And maybe you're starting with a flat line, right? That will be your initial set of parameters, zero intercept. And you just turn off the video. It's having some issues, right? So yeah, so what like I was saying, you may start with a zero intercept line, and then along with the fitting, both the slope and the intercept are changing, and this is the best fit. And this is what we mean when the model is learning, right? It's finding out what the data set is all about, and the fit quality is improving with each iteration, right? So the main point is that the loss function should reduce with each iteration. So if you plot the loss function as a function of the iteration, this is optimal learning, where you're able to reach the minimum point. This is slow learning, where it's really slow and it's not able to reach here, or it may take a too long a time. And then this is fast learning, like I said, like if your learning rate is too high, then you'll kind of explode, and you may never reach the minimum point. So you have to be careful how to choose the learning rate by making this plot between the loss function and the number of iterations. Now, there's also newer algorithms which have been developed. Gradient descent is not the only algorithm. And what is essentially happening in these different algorithms is that you want to reach the minima, but there can be multiple minima, right? So this is a local minimum, this is a global minimum, and we don't really know where the algorithm will reach. And some algorithms are slightly better at finding global minima, but there's no really foolproof way to find global minima still. I mean, that's an open area in optimization theory, right? So this is an animation of 5 different algorithms on a surface. You have gradient descent, which we talked about, but there's also others which use the gradients in slightly different ways. They have different names like momentum, adaptive gradient, RMS, prop, Adam, and so on. And you can learn more about these if you go online, or if you pick up any book on optimization algorithms, right? So as I said, the left well is a global minimum. There's really no guarantee you'll reach it. Most often than not, you will reach a local minimum, but there are some methods which are better at finding global minimum, right? And this is just a plot which shows you what I was talking about, right? So let's say you're trying to minimize this particular function. You start here, then if the learning rate is correct, you will kind of reach here in a reasonable amount of iterations or time. But let's see what happens if the learning rate is too high, right? You just kind of oscillate about the minimum, and you're never able to reach this point, like I was saying earlier. So this is just something to keep in mind as practitioners of machine learning. Now, how does one apply machine learning in their research, right? So the way, I mean, some people have kind of identified is as chemical engineers, and especially working in academia, we go from the concept of a material, then we synthesize the material, or we do some chemical reactions. We may have to make some devices like, say, a reactor, a battery, or supercapacitor or something, and then you have to test and characterize it, right? And at the end, there's a feedback cycle. The material didn't work, you may have to do it again. And this is also the kind of loop which is practiced in R&D in the industry, right? So many companies are developing newer products, and this is kind of the pipeline they follow. Now, it would be nice if we kind of close the loop by bringing in AI, ML, software, and robotics here, right? At each stage, machine learning can help. Let's say you want to discover materials, right? So you go to a whole database of materials, you try to apply an ML model, and you're able to find out which is the best model for your application. Maybe you're interested in batteries, so you're able to find that. Then in terms of synthesis, let's say a machine learning algorithm can tell you what is the best condition for the synthesis of that material, right? Do we do it at low temperature, high temperature, low pressure, high pressure? What about the pH, right? So many different things for a machine learning model to predict and help you out with. Again, in terms of prototyping, right, there the role of ML is slightly less. It becomes more like AI and robotics. Let's say if we have a prototype, can we automate the construction of this prototype and enable mass production of this? That's one idea. And of course, at the end, testing and characterization, of course, ML in the classical sense can help. If you have any plots, let's say you have cyclic voltammetry in electrocatalysis of batteries, then if you give the CV plot to a computer, can it tell you what all reactions are happening and which voltages they're happening at? So that's something for people to keep in mind. And then through this pipeline, ML can be applied really to any stage of the chemical discovery and application process. And as chemical engineers, we'll be quite appropriate to be engaging in this kind of work. Now, if you want to implement machine learning on your computer, then there are many, many libraries, and most of these, although they're also available in C, Java, and so on, but Python is kind of the preferred language for machine learning, and it'll be good if you can learn Python. So one kind of open source platform in machine learning is called RDKit, which is for chem informatics and machine learning. And chem informatics essentially means if you have a chemical molecule, how do you represent it in terms of features, right? So this RD kit has various features, various options to export a chemical molecule as a feature. Then there's also newer options. There's an open source Python ML library. So this is not just for chemistry or chemical engineering. This is for entire machine learning. It's called scikit-learn, and it has many different algorithms, regression, the decision trees, which we introduced, then boosting algorithms, everything is kind of available here and will be useful. So I just wanted to confirm, you're able to hear me, right?
Yes, sir, we can hear you, sir.
Okay, great, thank you. So then after scikit-learn, I wanted to introduce something called DeepChem, which is a platform for deep learning for materials and drug discovery. Let's say you're in the pharmaceutical industry, you're interested in making drugs, or you want to discover new materials, then this DeepChem is quite a recent platform and it's proving to be very useful in these applications. So these are just some of the different packages that you can keep in mind. Of course, there's others called TensorFlow and Keras and so on. And I think there was a question which asked, how can you develop ANN models? And yeah, you have to use these other kind of tools. There's TensorFlow, there's Keras, and all kinds of things. And they can help you use Python to develop and train your artificial neural network models. Right. So let's come to the topic of decision trees, which we very briefly introduced at the beginning of the presentation. Right. So a decision tree is a flowchart like structure, which is used in statistical and machine learning, and it consists of multiple nodes that lead one to the final answer. Right. And there are three types of nodes in a decision tree: the root node, where you start, then a decision node where you make a decision. So you choose one of two paths, and a leaf node where a value is assigned, right? So this can be the schematic of a decision tree. You start at the root node, then there are two options. There's a decision node, again, a decision is made. Then you come to the leaf node and you get some kind of a value here, right? And this chain can kind of proceed, and based on where you reach, you get some sort of a value, right? So this is just a schematic. Let's look at an example. So the question is, will you walk to work or will you take the bus, right? So let's make a decision tree for this, because it's going to depend on the weather. So if the weather is rainy, of course, you're not going to walk, so you'll take the bus, that's right. So this is like a decision tree here. If the weather is cloudy, then it depends on your mood, whether you're hungry or no. If you're hungry, you want to kind of stop somewhere and get breakfast or lunch, so then you're going to walk. If you're not hungry, then you don't need to stop anywhere, so you take the bus, right? And finally, if it's sunny, then maybe you look at the time. If you have a lot of time to reach to work, you then walk. If you don't have time, you don't want to be late, then you take the bus, right? So this is just an example, but really it works like this. At each point, there's only two types of decisions that can be made. Here, of course, there's three different ones, but in most cases, there's only two of them. So this is just an example to tell you what these decision trees are. And these are proving to be very useful in machine learning these days. And this is kind of the heart of the talk, where we'll introduce concepts such as boosting, bootstrapping, and so on, which are quite popular in the literature. And we'll understand how decision trees are helping us achieve that. right? So traditionally, decision trees have been known to be weak learners, meaning that there's only slightly better than 50 to 50. Is there a question? Someone is speaking. Okay. So decision trees are usually weak learners, which means that there's only a slightly better than 50 to 50 chance of predicting the right answer, right? So they're not very accurate. So that's why we want to improve these decision trees. We cannot use decision trees on their own. And this is where things like boosting and bootstrapping that is going to improve the decision trees, right? There are two ensemble-based
Madam, Kamichan
strategies
madam,
to
இன்னைக்கு
improve the
third
decision
இயருக்கு
tree
practical
performance.
first 2 hour நான் எடுக்கிறேன் லாஸ்ட் hour மட்டும் நீங்க ஏதாவது பார்த்து இன்க்ரீஸ் பண்ணுங்க 3 hour தொடர்ந்து கத்தாம
Right. So there are two ensemble-based strategies to improve decision tree performance. The first one is called bootstrap aggregation or bagging, where a consensus-based approach is used to improve the accuracy of the model, and we'll try to discuss that. And the second is boosting, which involves growing decision trees till they achieve the desired accuracy, right? So there's two different strategies, either a consensus-based approach or like growing and making the tree more complicated, right? So that's boosting. And there's one class of machine learning algorithms called random forests, and you may have heard about them a lot in the literature. And a random forest is essentially a type of bagging approach to create a strong learner from these decision trees, which, as I said, are weak learners, right? And what you do is you have, say, three different trees, right? Or maybe more, tree one, tree two, tree n. Each of these trees make a prediction, and then you take a majority voting. If you have a classification problem, you can do majority voting. If you have a regression problem, you'll just take an average of all of these, and let's say you get the final result. And what's so random about this forest, right? Each of these are only trees. What is making this forest random? Why is this a random forest of trees? And this is a random forest because each tree uses a random subset of features. So each tree may not use all the features. This tree may use 5 of the features. This may use 10 of the features. This may use all the features, right? So it's totally random which tree will use which features. And that's why this is a random forest of trees. And of course, while this randomness kind of increases the performance and this ensembling increases the performance, the kind of limitation here is that the random forests are less interpretable, right? Because everything is happening in a random way. You cannot say that this feature is kind of contributing more or this feature is contributing less. So decision trees are very interpretable, but random forests are quite less interpretable because of this randomness that is introduced in order to make the predictions better, right? So that gives you some idea of what this bootstrap aggregation or backing is, but we'll discuss more in the next slide. And later on, we'll also discuss in quite some detail what boosting is. Okay, all right. So what is bootstrap aggregation or bagging? So bagging is just a short form of B from the bootstrap and AGG from the aggregation. And there are two different words here, right? One is bootstrap, one is aggregation. So bootstrap means generating multiple data sets from an original data set using sampling with replacement. So what is sampling with replacement? Let's say you have a bag with some balls in it. There's 5 balls. Now, if you take out one ball randomly, you're left with 4 balls, right? Now, either you cannot put the old ball back or you can, right? So in bootstrapping, you put all the balls back and then you sample again. So this is what is meant by sampling with replacement. So that's bootstrapping. And then aggregation means combining the results of multiple ML models.
भूल जाता हूँ इसका मैं अरे जो अक्सर आता है बात करने कसरावत कर उनका है ना पीयूष पीयूष
Right. So aggregation means combining the results of multiple ML models, each trained using one of the multiple data sets that were generated during the bootstrapping process. So together you have this bagging, and let's just illustrate this with a schematic, right? So this is an original data set. Then based on sampling with replacement, you can have, let's say, n different data sets. So that's the bootstrapping part. And then the aggregation part is when each of these will make a prediction, and then you'll have an ensemble prediction. And the whole process is known as bootstrap aggregation or bagging. And this is a very famous method to kind of improve the robustness of the decision tree models, whether if you use a random forest or not. I mean, bagging is kind of independent of doing one of those things, right? So this is a very good way of increasing the utility and accuracy and robustness of decision tree models. The next set of algorithms, which is kind of what was given in the title of the talk, is boosting algorithms in ML. And why I'm so interested in boosting algorithms is because they have gained a lot of popularity in recent days, and they are very good in terms of making predictions, and training the models is also proving to be quite a fast process here, right? So what happens in boosting is that you combine a lot of different weak learners, right? Or models such as decision trees. You combine them together to generalize and perform better. And at each stage, you boost the model, meaning that you increase the number of weak learners, and then you put all of them together, and then they will do the task better, right? And in most cases, the decision trees which we introduced, they perform the role of weak learners, and new weak learners are iteratively added to the model to seek better performance from the model, right? So before we proceed, I just wanted to remind you of what the decision tree, as we discussed, there's a root node, then there are decision and lead nodes, and at the end you get a particular value or a decision. And then this was just an example that we had discussed a few slides back, where we had asked the question whether someone will walk or take the bus to work, and using this decision tree approach, we were able to make a decision. And similar things can actually be used in a chemical plant, right? Let's say you want to decide whether you want to ramp up production or not. You can use all these different questions to come up with a decision. That's why they're called decision trees. Now, there are many types of boosting algorithms in ML, and there are two main classes. The first is adaptive boosting, in which the weights of the wrongly predicted data points are increased as we proceed with the model training, right? So the model may predict some data well, some of it may not be predicted well. So once we start to know which are the data points not predicted well, then we can increase the weights of those data points to improve the model, and this is called adaptive boosting. And the package called AdaBoost, or the method called AdaBoost, was introduced in 1997. So that's been there for a while, and these days it's no longer the most popular method. The second one, which is these days very, very popular, is called gradient boosting. And here, decision trees are modified to improve the performance of the ML model as we proceed with the model training. And there are many, many different libraries that are available. These are all open source. You can use them in Python. One of them is called XGBoost, which came in 2014, then LightGBM in 2016, and CAT in 2017. And I'll discuss on the next slide what these different things mean. And let me just illustrate with a schematic what is meant by adaptive boosting and what is meant by gradient boosting, right? So as I said, in adaptive boosting, you start with the original data. Let's say you have a classification problem. So there's two predictions, yes or no. And then your model is making some predictions, but then you figure out that the model is predicting some of the data correctly, some is wrongly. So the ones which it is predicting correctly, you just remove, right? So that's the translucent circles here. And the ones which it is predicting wrongly, you kind of increase their weights, and then your model is trained again, you get some sort of a better performance. Then you again look at the ones which are performing still badly, and then you improve the model, and so on and so forth. And at the end, you can use an ensemble classifier, right? You can weight all of them, and maybe you give more weight to the later ones because they're able to predict the data points that were done wrongly by the initial model. So this is adaptive boosting. And then this is more like gradient boosting, right? So you have error as a function of iterations. And instead of just training the models or the coefficients of these nodes, you also add more nodes, right? So you add two decision trees together, or you increase the number of levels in the decision tree. So you not just change or tune the values of the nodes or the decisions made at the nodes, you also change the number of the nodes and the structure of the decision tree itself. And that is what is meant by gradient boosting. All this XGBoost, LightGBM, and all these things fall under this category, and they are proving to be very, very useful in chemical engineering and material science research, right? So let's compare this LightGBM and XGBoost to sort of understand what is going on behind the scenes and why one of them is better than the other. So the first thing is cat boost, right? So cat boost is mostly intended for categorical features. If you have continuous features, then cat boost is not so good. So you can decide whether you want to use cat boost or you want to use light GBM and XG boost, which are slightly more general than cat boost. Okay. Now, both light GBM and XG boost, as I said, are open source gradient boosting libraries, and both of these are available in Python if you want to use them and learn them. And the difference between them is that XGBoost uses level-wise tree growth, right? So let's say the decision tree was just like this, then you will add one entire new level here, and then as you proceed, you'll add more and more levels, and the complexity will increase, right? The other hand, light GBM uses leaf-wise tree growth. So instead of growing the entire level here as in XGBoost, you will only grow it node by node. Let's say only one leaf, you will add two nodes here, right? Then this leaf you will choose and you will add. So you'll no longer add so many more nodes at the same time. So you see that light GBM gives you the sort of granularity that you need to train an ML model more accurately, because it grows leaf-wise rather than level-wise. And these are some of the advantages of light GBM over XGBoost. It has reduced training time, of course, because if you're not adding so many newer nodes, you're adding only few of them, so it will reduce the training time, and that will also lead to better parallelization, right? Because here you can you know that you're not modifying this part of the tree, right? So you can only operate here, and that can increase parallelization. Whereas here, if you do level-wise tree growth, then all the nodes are getting modified, and you can't do parallelization so much. The third is there is increased complexity of the tree due to more granularity, right? So in some sense, you have a lot of granularity, and you can choose exactly which node you want to add new like sub nodes on to increase the performance. So light GBM generally is better because it uses leaf-wise tree growth as compared to level-wise tree growth in this XGBoost. And these days, a lot of people are using light GBM in their research work, right? And finally, before going on to the applications part of my talk, I want to introduce a concept called k-fold validation, right? So let's say that you have a big data set here, and you have divided the data set into 5 different parts, 1, 2, 3, 4, 5, right? And what is meant by k-fold validation is that each data point will contribute at least once to validation, right? And it may contribute many times to the training. Uh, for example, what happens here is that you train using the splits, right? 2, 3, 4, 5 of the model and validate with 1. Then you train with 1, 3, 4, 5, validate with 2, and then so on, right? So this is a 5-fold validation. Of course, you can also do 10-fold, 15-fold, depending on your needs. And what this means is that each data point is participating both in training and validation, and this leads to more stable models or better models. And in the end, you can do some kind of ensemble, just simple averaging to develop your ensemble model. So this k-fold validation is slightly different than the bagging thing, which we discussed earlier, right? So that was just sampling with replacement and then using ensembling. Whereas here, it's different. Each data point will participate one in training and one time in validation, and then you can kind of obtain an ensemble model here. And this is essentially a means to generalize and to make machine learning models more robust by using each data point for both training as well as testing applications, right? So are there any questions at this point which someone wants to ask?
So there was a question from Dr. Lavare, which is ML software for process control system.
So I'm not very well versed in process control, and I've not worked in that area. So I wouldn't be able to answer that question, but any of the other researchers in India who are working in process control, I think they'll be able to answer that question. Right. Any other questions, Dr. Ramakrishna?
Sir? Hello?
Yeah. Go ahead.
Hello.
Yeah, we can hear you.
Am I audible to you, sir?
Yes, you are audible. Dr.
Sir, I'm Dr. Ajit Lavre from Vikhi Patil Engineering College, Ahmednagar, Maharashtra.
Uh-huh.
Sir, actually, in the process control system, say suppose level control system is there. Okay. If I found the model, means either first order model or second order model or with the date time model. So what I am doing, I'm collecting the input and output data. Okay, sir. And after collection of the input and output data, using system identification toolbox of MATLAB, I am finding the that modeling equation of that particular process control system. So I am having input data as well as output data. Okay, sir. So near about 40,000 data means point data I am having that one. So what is my question, sir? How we can apply the machine learning algorithm to that data to extract the faithful data so that my system performance will get improved.
I see. So how many like independent variables or features do you have in your data set?
Yeah, only one time is the independent variable, sir. No doubt here. And whatever the input data is there, that I'm applying the voltage and I'm taking the level of that particular tank level actually.
I see. Okay.
Yeah. So my question is that basically your this topic is very interesting, and I want to apply the machine learning algorithms to that process control system.
Correct.
So how we can use ML techniques to extract the faithful data?
Correct. So what I would suggest is that Python is a good language to start with. So at one point in the slides, I'd introduced this scikit-learn, right? So that would be kind of what you should go to, right? This open source Python library, scikit-learn, it has all the different types of regression, decision trees, and so on. And my recommendation would be to start very simple. Just start with linear regression, right? See if linear regression can predict the output as a function of the input. And if not, then you go to more and more complicated models like these decision trees, right? But usually you will need at least 10 features or so for some use of decision trees, right? Because you want some subsets of trees. So maybe 5 or 10 features, but I think you have at least 5 features. So you can kind of go to that level as well. So just start with scikit-learn. This has some basic decision trees, and then you can also bring in the new things that I was discussing, the gradient boosting like Elite GBM. They can also be directly interfaced with Python, and you can start using them.
Okay, sir. Okay. Thank you, sir. Thank you.
Great question. Yes. Okay. If there are no further questions, then yeah, let's go back to the k-fold validation technique. And this is basically, as I said, a means to generalize and make the machine learning models more and more robust by using each data point for both training as well as testing. And this is something I recommend that you do when you're developing machine learning models, right? So with that, let's move on to some applications. So enough of all the theory and all the background and what machine learning is and what is gradient boosting and so on. Now let's go on to the actual applications in chemical engineering which can be done, right? So all of this started to be applied around like 2015, after 2010 in chemical engineering applications. So one of the first papers which tried to use gradient boosting was to predict the structure activity relationships of APIs, right? So you have active pharmaceutical ingredients that are used in the pharmaceutical industry. And based on the structure of the API, you want to predict what the activity of that molecule is, right? And what this means is you'll have different features. The structure can be condensed into many features, like how many atoms there are in the molecule, how many carbons there are, how many hydrogens there are, right? How many oxygens there are, what is the size of the molecule. So all these things will come as a feature. So that's the structure. And then activity, of course, is one variable you want to predict. And what these people showed is that if you used boosted decision trees, then the performance was very, very good, right? And that's why they were able to make this study. And if I'm not wrong, I think they also involved some people from the pharmaceutical industry in this paper, right? Then in 2017, gradient boosting was used to predict the thermodynamic stability of perovskites. So as you know, these perovskites are these days being explored for a number of applications, whether it be solar cells, that is photovoltaics, or even for photoelectrocatalysis. And more often than not, it is not known whether a particular perovskite of the formula ABX3 is stable or not. So A, B can be transition metals, X can be oxygen or halide, and so on. But it is not known whether you can make it in the lab or not. So the question is a particular ABX3 perovskite stable or not? So what Schmidt et al. Did in this paper published in Chemistry of Materials is that they developed a density functional theory based gradient boosted machine learning model to predict the thermodynamic stability. And how would you guess the thermodynamic stability? Based on the formation Gibbs free energy as well as the phase diagram of the compound. So based on the phase diagram, the Gibbs free energy of formation, you can predict the thermodynamic stability of perovskites. And this was again a major advance because only if you know whether a material is stable or not, can you aim to synthesize in the laboratory, right? Without knowing whether it's stable, let's say material is predicted to have very good properties, but you can't synthesize it, then it's not very useful to us, right? So that's why as chemical engineers and as people developing newer chemicals, newer materials, this kind of work is very important to us, right? And then again in 2017, this Isaev et al., they published in Nature Communications, and then they predicted the electronic properties of materials as well as some mechanical properties, I think. And here is a plot of insulators and metals, and they're using two kind of features in this plot. On the y-axis, you have the heat of fusion, delta HF, and in the x-axis, you have the molar volume, right? And as you can see, some kind of structure or clusters emerge. The blue points here are metals, the red points here are insulators. Of course, there's some spread here, but they were able to show that with the gradient boosting, you're able to correctly classify a material as insulator or a metal based on these different metrics here. So you can see very innovative uses of gradient boosting as applied to chemical engineering and material science, where you can know the properties of the materials, their thermodynamic stability, as well as the activity of pharmaceutical active ingredients, whether they are active or not, right? So these are very good examples of applications. Then moving on after 2017, there's also one work by Evans and Coudert in France, which predicted the mechanical properties of zeolite materials, right? As you know, zeolites are these days gaining a lot of importance, not just for composite applications where the mechanical properties are involved, but also for separations and adsorptions, right? Because they have an ordered structure, and then you can adsorb a lot of molecules and also separate them. And what these researchers did was they used gradient boosting to predict the mechanical properties of zeolite materials. And they used features such as the density, the volume, the space group to which the material belongs, the surface area, pore volume, pore size, and the dimensionality, right? And they used all of these features to predict the mechanical properties. And again, this is going to be useful for people working in polymeric composites, right? If you can know the mechanical properties of a material a priori, then you can decide which is the best additive you want to add to your chemical or to your polymer, right? And people working in, say, Unilever or other companies or petrochemical companies, they may be interested in additives. And again, machine learning is going to come very handy, because if you have like thousands of additives and you want to find the best one of the ways to find that out is through machine learning. Now, in this work by Adiuka et al. In ACS Sustainable Chemistry and Engineering, what they were able to predict is the projection of organic municipal waste, right? And these days, as landfills are increasing a lot, we know, I mean, there's a big landfill problem in Bangalore. The landfills are overflowing. And the way to kind of avoid that is what is being practiced in many of our homes now. We have waste segregation. The wet waste is separate from the dry waste. And if we can develop a model that can project the organic waste, right, as a function of time in a particular year, then we'll know at what point we need to have some kind of intervention strategies, when we can compost more and provide fertilizers to the farmers, and so on, right? So this was a gradient boosting model that was able to predict or project the amount of organic municipal waste that is being generated. Okay, so that's quite an interesting study. And then after that, in 2018, we have another study which was able to use different features of proteins, like what sequence is there in the amino acids, the more structured features like alpha helix, beta helix, alpha pleats, and then energy features and exposure features. And with these kinds of features, they were able to predict hotspots at protein-protein interfaces. So hotspots meaning that when two proteins come close to each other, how do they bind or how do they interact with each other? That kind of interaction is called a hotspot. That part in the protein is called a hotspot. And through these training and testing data sets, they were able to predict these hotspots at protein-protein interfaces in quite a reliable manner, right? Then there are more examples. There's this review paper by Schmidt et al. In NPJ Computational Materials, where they actually review the use of machine learning in material science, how you can collect the data and then clean the data. And one major part of it is selection of the algorithm, which algorithm you'll use, right? Even today, we discuss so many algorithms. There's simple regression, there's simple decision trees, there's bagged decision trees like random forest, there's boosted decision trees like adaptive boosting, then light GVM, and different models. So which model or which algorithm do you use? So right, that's one important question of all of these things. And then of course you have training data, you have test and validation data, and of course you'll have to pre-process the data and then train it, and then you'll have the final model, and you can make some new predictions, right? Which is what we've been discussing, how we can impact application in the real world or in the industry through our knowledge of machine learning and chemical engineering, right? One study you may find interesting is this study published in INECR by Jiao et al. In 2020, where using a database, they were able to predict quantitatively the flammability of mixtures. So let's say you have organic molecules, and then you know the conditions in which they are present, what is the temperature, pressure, concentration. Can you predict whether the mixture will be flammable or not? And again, through the use of gradient boosting, these authors were able to convert a database through gradient boosting to these quantitative property consequence relationships to predict the flammability. And from a safety perspective, this can be very, very important, right? There's lots of incidents of fire, and if we can know in a chemical plant what is being leaked or exposed or what's the conditions, we can avoid such incidents and save human life, which is, I mean, in a plant, it's very important, and it's the foremost thing that should be done. Now, another study which was published recently is about heat transfer in oscillating heat pipes, right? And as you may know, heat pipes are a technology which have been proposed for some time now, which is to improve the rate of heat transfer based on convection heat transfer. And what these authors did was, based on the flux and the temperature and the heat transfer coefficient, they were able to propose a gradient boosting model, and which was able to predict this heat transfer coefficient, right? So there's lots of innovative areas where this can be applied. This is more related to conventional chemical engineering, where you can increase the heat transfer rate by kind of developing a model. This is also more chemical engineering in a plant. You can predict the flammability and safety standpoints of what is happening. And of course, this is more from a material standpoint, but as more and more chemical engineers work in the area of polymers and materials, this is also going to be important for us to consider as we move into the future. Then there's also more examples that I want to point out. And the entire reason for discussing these applications is to give you some flavor and some picture of what is happening in the modern day literature, right? And we cannot do research in a vacuum. We have to kind of be aware of all these new developments. So one new study looked at the mechanics of graphene oxide functionalization. As many of you may know, graphene oxide is an important material, nanomaterial, which is now being used in several applications. And using gradient boosting, these authors were able to kind of predict different properties like oxygen to carbon ratio and the fraction of epoxide group. And then through that, they were able to predict the mechanical properties of graphene oxide with this kind of a functionalization, right? So that's another interesting applications. Then more related to chemical engineering, we've had work which predicted the caking ability of coal blends, right? So based on 140 different coal blends from experimental data and additional coal samples, they got like 290 samples, and They use 80% of these samples for training and 20% for testing. And through this XGBoost model and the set of features, they were able to predict these different indices that quantify whether the coal blend will cake or not. And that's an important consideration for chemical engineers. And finally, there's been one study which has predicted the gas hydrate formation temperature. And as you can see through this gradient boosted training model, they've been able to obtain very, very good agreement between temperature, which is experimental, and they predicted temperatures. And this is again some kind of a model which will be useful in understanding when hydrates will form and how we can utilize them in useful applications. Right. So with that, I'd like to come to the summary of my talk. I first introduced machine learning models, and I said that they aim to predict complex data based on features. Ultimately, we'll get some kind of a parity plot. So while you can have the actual data on the x-axis, the predicted data on the y-axis, and then if your plot is close to y equals x, that means you're doing a very good job. And then each data point, of course, there'll be many features and many values, and you have to combine these features to make the prediction. So that's what ML is all about. Then I discussed the use of the gradient descent algorithm and how you can train the parameters in the ML model. I also discussed the concept of the learning rate and how if your learning rate is too high, that means you can overshoot. And if the learning rate is too slow, then you will not reach the minimum point in terms of the error. So the best way is to kind of plot the loss function as a function of the iteration number and find out. And we also discussed three different types of loss functions: the L2 loss, L1 loss, and the log loss. But of course, there's many other kinds of loss functions that you may find useful in your own research. Right. Then we discussed the boosting algorithms, which combine weak learning decision trees to create a robust model. And we said that LightGBM is one of the most popular libraries and was introduced in 2016. We also discussed how you can do different machine learning models, how you can train them. So we introduced things like the DeepChem and the Open RDKit, as well as the other Python libraries. And finally, we also discussed the difference between LightGBM as well as the XGBoost methods. We also introduced bagging and k-fold validation, which can be used to make models more reliable. We discussed that bagging is a combination of bootstrapping and aggregation. And then we discussed how k-fold validation means that each data point will contribute to both training as well as testing the algorithms. So with that, I'd like to thank my institute, IISc, funding sources, National Supercomputing Mission, my group, as well as my student Rahul Sheshnarayana, with whom I'm doing some machine learning work. And I'd like to thank you for listening. I'd like to thank the organizers for this nice opportunity to connect with all of you. And I'll be happy to take any questions that you may have.
Yeah, thank you very much, sir. It is a wonderful session.
Thank you, Professor Ramakrishna. My pleasure to be here.
Yeah, thank you, sir. The participants, now the session is open for question and answers. Sir, I've got a question from one participant, Tulsi Vyas. How can we calculate optimum learning rate?
Right. So the way to calculate the optimal learning rate is by plotting the loss function, right, as a function of the iterations. And you need to visually see what is happening, right? Without the visual inspection, it's difficult to predict the optimal learning rate. Of course, many times you don't bother too much to do that, but that plot is a very important way of seeing what exactly is happening. And there you can see if there's a divergence happening or some kind of a convergence which is happening. And that will tell you what's the best learning rate that you should have in your work.
Yes, sir. I'm still expecting some questions from the audience.
Mhm.
Yeah, the participants, you can ask the speaker about your questions. Yeah, the participants, you can unmute yourself and ask the question directly to the speaker. Sir, I hope there are no further questions. I think the participants might have clearly understood. Personally, I myself working on modeling and simulation of biological processes. So I would
I
like to
see.
ask you one question, sir. So can you please explain how can we introduce this machine learning concept in bioprocessing?
Right. So I'm guessing by bioprocessing, you mean like production of use of microorganisms to produce biological enzymes, things like that, or is it something different,
Yes, sir.
Professor
Yes, sir.
Ramakrishna?
Yes, sir. Yes, sir. It's the same.
Okay, right, right. So it's more biochemical engineering. So that would make me guess that you want to predict, say, the yield or the selectivity of a particular enzyme which is being produced as a function of the reactor conditions, what microorganisms there are, what is the temperature, pressure, what is the stirring rate in the reactor, what is the inlet composition, all these things, right? What is the metabolism rate of the microorganism? So all these things should enter the model. So you first have to figure out what it is that you want to predict, right? So let's say we know what we want to predict. That will be the first step. The next step would be to find out what are the variables on which that quantity can depend, right? Once these two things are clear, then the best way to start is to come up with first a linear regression model, right? It's always best to start at the most simplest method, right? Because you never know. The simplest method may give an answer, so then there's really no need to make things more complicated than that. Yeah, it's often best in science to search for simple answers. So we can start at linear regression, and then if it doesn't work, then we can go to the more complicated models like decision trees and then boosted decision trees, right? Like this XGBoost and so on. So that would be my way of going about it. And yeah, if there's specific data, then it'll be possible to look at what exactly we want to do based on the features and based on what's there. And I mean, in some cases, there's also other kinds of things you may want to do. Things like principal component analysis will tell you which variables are the most important. When you do things like boosting and decision trees, there's feature importance, right? So you can make a plot of each which feature, right, versus the importance, and it may tell you, okay, the temperature is more important, or the pH is more important, or the metabolism rate is more important, right? So a priori it's difficult to know what thing is more important, but that's one of the things in machine learning, that you can predict the feature importance as a function of uh, the different features. That will tell you which features to include in the model and which ones you can exclude. Does that answer your question, Professor Ramakrishna?
Yes, sir. Yes, sir. Thank you. Thank you very much,
Oh,
sir.
great.
Yeah.
Definitely.
Sir, there is a question from Ms. Anita Maglicherla. So in k-fold validation, shall we need to take simple average of model finally?
Right. It is advisable to do so because once you have made 5 different models, then it's best to kind of take an average of all of them so that each model will help you obtain a more ensembled answer, right? Always a consensus-based approach is better than just relying on one model. So I would say that it's better to take simple average of the modeling. Of course, you can also explore things like weighted averaging, right? Maybe you weight some models more, but unless there's a very good reason to do that, right, in terms of some data being more reliable, some being not, uh, really, I mean, simple averaging is the best way to go about the things.
I hope it answers
Right.
Sanita. Sir, there is a request from Mr. Tulsi Vyas. Sir, if possible, may I have your email ID for further guidance?
Right. Should I type it in the chat box or?
Yes, sir. Yes, sir. Yes.
Right. So I will just type my email address in the chat box. And yeah, if anyone has any questions, if you email me, I'll do my best to try and answer that.
The participants, if you have further questions, you can raise it with us. Yeah, sir, I hope there are no further questions. So I would like to thank you for your exemplary lecture on boosting algorithms, sir. So I would like to give a vote of thanks in the formal way. So at the outset, on behalf of organizing team extend my sincere thanks to the session speaker, Professor Anand Govindrajan, for his exemplary speech on Introduction to Boosting Algorithms in Machine Learning topic. Through his topic, he has elaborated the specific applications of machine learning in the chemical engineering research, which would definitely help the faculty as well as the research participants to take up the problems in the chemical engineering with the help of machine learning. So through his talk, he has enlightened us with machine learning algorithms categorization, and he has given us many examples on supervised and unsupervised learning, and also made us to how to draw the decision trees in machine learning as well as the bootstrap aggregation in the machine learning. And also he has explained neatly about how to train and test the models using k-fold validation. And also he has enlightened us with gradient boosting for chemical engineering applications with many of recent cited literature. Thank you very much, sir, for your excellent lecture on this.
Thank you very much, Professor Ramakrishna. It was a pleasure to be here and to interact with my faculty colleagues and with everyone who was attending. And hopefully, we'll get more opportunities to interact in the future. Thank you so much.
So next, I would like to extend my gratitude to the AICTE Training and Learning ATEL for providing the financial support to conduct this online FTP. And I also extend my sincere gratitude to the management of MVJ College of Engineering, Principal, Vice Principal, College of Engineering, Controller of Examinations and Registrar, and IT Help Desk for their constant support throughout this session. At the end, I would like to express my sincere thanks from the faculty participants who have attended all their way to all these sessions with great difficulty and with more interest. Thank you all the participants. Thank you very much, sir. So we hope the same kind of contribution and you extend greater support in the future whenever we need, sir. Thank you very much.
Definitely. Thank you to all the participants.
Participants, we have next session at 11:30 by Mr. Ravikiran, Senior Process Engineer, Grace Division Chemical India Private Limited, Chennai, on the topic Digital Twin Application for Steel Refining Process Modeling and Optimization. We expect you to sign in by 11:25 so that we can start the session at 11:30. Thank you all.
என்ன டிப்ஸ் கொடுக்குறீங்க
ட்விஸ்ட்டுங்களா? ட்விஸ்ட்லாம் ஒண்ணும் இல்லைங்க மேடம்.
வாண்ட என்ன சொல்லுது? இப்ப எங்க இருக்கீங்க?
இங்கதான் மேடம், கரூர்ல தான்.
பரமத்தியா?
இங்க நம்ம முனியப்பன் கோயில் இருக்கு இல்லைங்களா, கரூர் போற வழியில ரவுண்டானா, அங்கதான் இருக்கு.
வீரங்கியா?
ஆமா.
அப்ப முனியப்பன் கோயில் ஸ்டாப் தான் நான் இறங்க ஊருக்கு போயிட்டு வரீங்களா? அப்ப என்ன காலேஜ்ல இருந்து கூட்டிட்டு போலாம், எத்தனை மணிக்கு கிளம்புறீங்க?
காலேஜ்ல இருந்து எங்க இவர் இருக்காரா, ராஜகோபால் தெரியுமா? அவர் தான் கூடவே வர்றாரு குத்திக்கிட்டு ரெகுலராவே அவர்
Good morning, Ravikiran sir.
Hi, good morning.
Sir, please check your PPT whether it is visible. Like, can you share the PPT so that we can see?
Okay. Let me share my screen.
Yeah.
Let me know if you're able to see my screen.
Yes, sir, I can see yours. Sir, can you please put it on slideshow mode? Yeah. Thank you, sir.
Is it visible now?
Yes, sir, it's visible and your audio is also clear, sir.
Okay, I'm trying to
Sir, we'll wait
maximize.
for another 10 minutes so that the participants will be coming back.
Yeah, okay.
And we'll
no
start the session exactly at 11:30, sir.
Okay. Is it necessary to turn on the video?
Sir?
Do we need to turn on the video?
No need, sir. So it's your comfort, sir. If you would like to share your video, you can.
Okay, fine. So how
Sir,
to
we
turn
start
on?
at 11:30, sir.
Okay. I'm trying to look at how to turn on the video.
Yeah, can you please switch on your video, sir, so that we can see?
Once it's shared here, yeah, I think it's it here, right? Start. Are you able to see me, right?
Yes, sir, we can see.
But let me turn off background.
Yeah, you can change that in the settings, sir. Yeah.
Okay.
Sir, Sagina ma'am is with me, sir. So you can see
Yeah,
her.
I'm.
Yeah.
Hi, sir. Nice to see you.
Yeah.
Hi, Sayana.
Sir, we'll start at 11:30, sir. So till
Yeah,
that you
sure.
can hide your videos, sir.
Sure. Thank you.
ஹலோ அப்படியா? வேற நம்பர்ல இருந்து வந்திருந்ததா? முந்தா நேத்தா? அப்போ இந்த நெட் இது யோப்பா இந்த நெட்டு இது யூஸ் பண்ணிட்டு இருக்காரு. இதுல ஒரு செமினார் மாதிரி அதனால அது கட் ஆயிடுதுன்னு நினைக்கிறேன். ம். ஆ சொல்லு. இனிமேல் தான். பார்த்தே முகம் சேஞ்சேன். ஒன்றும் இல்லை வேற.
Sir, Ravikiran sir. Can you hear me, sir?
Yeah, I can able to hear you.
Yes. We'll start the session, sir. It's 11:30. The participants have come back.
Okay.
Yeah. So good morning, one and all. So I welcome you back to the fourth day's second session of 5-day virtual Atal FDP being conducted at MVJ College of Engineering, Bangalore. So on behalf of the coordinating team, so I welcome the current session speaker, Mr. Ravikiran Anapaganti, and also other faculty participants for this 11th session of Faculty Development Program. So I, Dr. Ramakrishna, Associate Professor of Department of Chemical Engineering, MVJ College of Engineering, take this opportunity to introduce the current session speaker, Mr. Ravikiran Anapagaddi, Senior Process Engineer R&D from Grace Division Chemical India Private Limited, Chennai. Mr. Ravikiran has obtained MTech in Chemical Engineering in the year 2011 from Indian Institute of Technology, Madras, and BTech in Chemical Engineering from JNTU, Kakinada. Presently, Mr. Ravikiran is with Grace Division Chemicals Private Limited, Chennai, since October 2014 as a Senior Process Engineer R&D. Prior to joining Grace, he was associated with Tata Research Development and Design Center, Pune, as a systems engineer from 2011 to 2014. Mr. Ravikiran has also been honored with many awards. One of them, On-Spot Award for his outstanding contribution to the organization, Tata Research Development and Design Center, TCS Innovations Labs, Pune, in the 2 consecutive years, 2013 and the 14. He is also a recipient of Srimati D.L. Saraswati Memorial Award with Silver Medal and Michael Bosch Prize with Silver Medal for the Best Project Presentation, and Dr. K. Subbarazu Memorial Prize with Silver Medal for the Best Academic Record in the Chemical Engineering while he was pursuing MTech in IIT Madras in the year 2011. Mr. Ravikiran is also an expert in modeling and simulation of physicochemical systems with sound knowledge of fluid flow, heat transfer, thermodynamics, chemical kinetics, numerical methods, developing computer codes and analysis of simulation results, identification of bottlenecks, supply chain management, data analysis, and visualization. Over the years, Mr. Ravikiran had also treasured significant experience in predicting critical operating conditions to achieve higher productivity, prediction of critical operating conditions to achieve higher productivity, and much more. So his core competencies include thermodynamic analysis, gasification and combustion, multi-phase modeling and simulation, data analytics and machine learning, secondary steel making, process simulations and process modeling, computational fluid dynamics, basic and detailed engineering, bottleneck and debottlenecks, CapEx and OpEx. Through his aptitude for continuous learning, Mr. Ravikiran had also secured many patents and authored many international publications and given many invited talks across the country. Now in this session, Mr. Ravikiran is going to deliver a topic titled Digital Twin Applications for Steel Refining Process, Modeling and Optimization. So with this brief introduction, I request Mr. Ravikiran to take over the session and enlighten us with his understanding in the area of digital twin applications for the steel refining process. So with this brief introduction, I request Mr. Ravikiran to take over the session. Thank you. Thank you, sir.
Thank you, Dr. Ramakrishna, sir, for your brief introduction, and thank you so much for giving opportunity to present my work during this virtual conference, FIDES conference. And good morning to all. Myself, Ravikiran, as Dr. Ramakrishna has introduced, and please, one more point before I start, please don't call me sir and just call me Ravi. That's much better than calling me a sir. And I think let's straight away go for the discussion and the presentation of the today's topic. And if you have some questions, feel free to ask me and stop me and ask me the questions before we move on to the next slides. So let's see what is digital twins. Basically, now name itself says different in terms of wording, right? So typically, what you guys might have got understood that what is digital twin, how does that differ compared to the current situations or current tools that we have in hand. Not only for chemical industries, but a lot of industries have their respective tool for solving the respective physics of the problems. So the even though wording is something different, but the background of the physics or calculations that are happening in the digital twins is the same what typically we do in the day in day out calculations. Let me introduce the digital twin. So the digital twin is like a digital representation of the physical objects or system that is in the system in the plant, or it could be any industries. So for example, let's take you have kind of chemical industry which has pre-processing, reactions, and post-processing and packing systems. So if you're trying to simulate overall entire plant or individual operations, we typically select a kind of mathematical model solvers or some kind of simulation solvers or CFD to resolve a particular objective. That means that we're trying to solve a real system in front of a computer digitally. So that itself is called a digital twin. It's nothing more, much more difference. But apart from the simulation, there are different ways to solve digital twin oriented problems through digitally, such as based on the data that we have. So if I conclude here on the introduction of the digital twin, so it's not only based on the physics-based simulations, it's also can be based on the data-driven based approach or integration or combination of both. So you already, I think you might have understood what is physics-driven based models. So that is basically we solve a first principle of the equations to solve any kind of physics equations. For example, if you want to solve a reaction kinetics or a reaction conversions, typical what we do is that we take the kinetics equations and solve uh, with respect to time how the conversion is changing for the CSTR or PF reactor or any kind of batch reactor or condenser reactor. So that is, we take basically the physics, first principle of the physics. If you don't have any kinetic informations, but you have conversion versus that time, what typically we do in the labs during our bachelor's degree or master's degree, we typically measure the concentration, try to estimate the kinetics using numerical techniques or some kind of fitting the first order or second order equations and try to identify the orderness and also the reaction kinetics, right? So it's the similar way where what we did is that we have taken the real data and try to manipulate or correlate real data in terms of a physical equations. So that is called a data-driven approach. So I think you now I think you understood what is the difference or basic understanding of the digital twins. Now coming to the digital twin, these days, I mean, a lot of people are talking about machine learning algorithms or ML, or data analysis or data science or digital twins. I think you will get to know how the digital twin evolved and from where it was started and what is the status right now. You can able to see the next slides, but all of them, I think most of the time we typically use it, but we will not call them as a digital twin or digital science. But apart from what we did, but it's much more higher. I think you might have seen, I mean, last 3.5 days or 4 days, you might have seen what all algorithms are available in the data science approaches, right? Typically, in our calculus, we typically use a linear regression equations to solve the uh, kinetic equations or identify the kinetics of the process systems or process. But we are much more beyond that. There are multiple machine learning algorithms are available to understand or estimate or predict the kinetic forms of the equations. And this digital twin has been applied to entire plant. It's not that only for process industries, but this digital twin can apply for any kind of industries. It can be a software industry, or it can be mechanical industry, or it can be civil industries, or it can be any kind of industries. But coming to the digital twin, there are three main subdivisions. You can see here. One is on the plant digital twins. Let me highlight point here. So one is a plant-oriented digital twins. Typically, what a plant-oriented digital twin does is that it try to identify is there any equipment failures or is there any capital investment is needed to meet the required demands or such kind of process simulations. And second category will be the operational excellence. It could be a planning type of models. I mean, how to schedule the production plan or how to minimize the logistics, how to design the control and optimize the plant production to meet the required quality or yield of the product. Such kind of things are divided into operational excellence. And operational integrity will be like kind of identifying the risk analysis, process analytics, and equipment failures or analysis. So this is the kind of a broader subdivision, and this division may or may not applicable for all the industries, but typically this kind of classification will help us to identify which category of the digital twin problem that we are applying it. Because it's not that all category of the digital twin applications may need a physics equations or may not need a physics equations. For example, let's take a case where you're trying to schedule a plant production to meet a required demand. It doesn't require any physics. It just needed only the time required or residence time of the individual operations and try to see or minimize downtime that is happening in the plant. Similarly for the scheduling it. But when you try to solve when particular equipment is down and what was the cause that was happened to make equipment is becoming a down. So if you want to see that kind of simulations, that it could be a operational integrity to identify the reason for making the equipment is down. Or if you look at kind of improving the, like let's say for example CSR, if you are trying to improve the mixing, so and how can we improve it? So you can do some kind of digital twin oriented simulations to understand physics that's happening within the CSTR reactor to improve their mixing index basically. So that we call it as a planned digital. I hope you got clear what it means of digital twin. Is there any questions before we move on to the next slide?
கனெக்ட் ஆடியோனா நம்ம பேசுறதா?
Sir, there are no questions being asked by participants.
Thank you.
So we'll wait for some time.
Sure. Okay. And also I'm trying to keep my video because network becoming slow if I have a video.
Okay, no issues. So you can switch off your.
And let's move on to the next slide. If there is no questions on the introduction part, let's see when the digital twin is started. It was started during the 1970s by NASA to prepare a technology for the Apollo 13 missions. And all the way over the years, the application of digital twin is growing a lot. Up to 2011, you can see the slope, how it is growing and what all applications were used to solve real systems or real industries. You can see started from the computer simulations, all the way started to simulation applications. And this, then around 2015, it will be around simulation driven systems. And now people are going more rapidly in terms of digital twin applications. And one of the key players are basically GE and also Siemens. And now we are also trying to enter into the digital twin applications. And basically, whoever doing Aspen simulations, we call them as a digital twin, but it's not exactly digital twin, but it's kind of similar digital twins. And also, whoever doing CFD simulations, that could be a part of digital twin because we are solving the physics equations, but the terminology or the something that we need to update on top of the CFD simulation that we did on the solving of physics equations. And coming to the how does this digital twin look like if you're trying to solve a plant oriented simulations? For example, if you see in the bottom picture, this is a real physics plant. We call it as asset, and how this asset within the plant is moving from one unit operation to other unit operations are represented digitally in the digital twin applications. You can see the clear example here. How does and which are the areas can be used to predict the required output from the each plant. And when we have this digital twin, it's no need to go to the plant to see and what's happening and what is current situation, what is current status. We can just sit at our office and identify the performance of each process within the plant itself, either from the laptops or either from the mobiles or either from watches. These days, Apple is one of the watch where we can integrate plant control system directly to the watches also. So there are applications to do it, but this digital will help you to understand how the material is transferring from one side to other plant or other unit operation, and what is the qualities, what is the yield that is coming out of each individual operations. So this kind of I think it's what I can say is that digital twin is like replication of the physical man to the digital, what do you call, robot. So it just simply, it's because, see, for example, if you want to control any quality in the plant, you will be able to see multiple people working around the same unit operation or within the plant. But if you have a digital twin, the number of people can also reduce. That's one of the drawback. But definitely the opportunities in converting entire plant physics asset into the digital twin is very good challenge, because most of the industries are trying to move towards the digital twin applications and also the data analytics approaches and science to improve their process, to understand their logistics and the supply chain, and also various kinds of level of calculations to improve their profitability from the plant. So with this, let me introduce the topic, that is a secondary steel making process. But I hope if the students or anyone is there, I think they may have studied the manufacturing the steel industry, steel from the steel industries. But let me give you a brief background how the steel was manufactured. And the raw material for the steel manufacturing is iron and the coke. Basically, so the iron was basically the iron is in the form of solid that was going to the blast furnace, which converts into the solid into the liquid with the help of burning of coke, and getting heat from the coke to the iron to the solid iron, which can convert solid to the liquid. Then iron has more amount of carbon content, and if you reduce the carbon, the iron will be converted into steel. So there is a series of operations before it converted to steel. So they have some particle removal and also the other ingredients such as the sulfur, nitrogen, then carbon. So once the carbon is achieved the required percentage of the steel, then it is called as a steel. So it's a raw steel, base steel that is going to be steel refining process. At the steel refining process, what they do typically, they add some kind of alloys to meet the required steel chemistry at the end of the casting process. So here the most of the things, if you look at, there is a very good opportunities in terms of developing a models, because one of the key industries is iron and steel, metals and metal industries. They do not have more versatile models developed, physics-based model or developed for understanding the current situations and current level of physics understanding as well as the modeling, solving the physics to the model. And also there is a very challenge in terms of resolving the current issues and also getting the right data because of the operational conditions that they have in the manufacturing any metal industries, especially for iron and steel industries. So as I said, once the steel was prepared from the iron by after removing the carbon, and it is going to the ladle refining process. And if you look at here in the right hand side picture, top picture, that is the combination of ladle and followed by the casting. So ladle have liquid molten steel, and it is a batch unit operations. And once the ladle operation is completed, it's going for the casting process, which is the continuous process. So to convert batch to the continuous, there is a unit of called tundis, which is intermediate vessel which can convert from batch to continuous by controlling the level of the tundis. So currently we focus only on the ladle, and I don't want to focus on the entire process because there are a lot of challenges within the ladle to resolve it. And here the objective will be basically, we want to uh, minimize the unwanted material present in the stream, such as the sulfur, nitrogen, oxygen, phosphorus, and so on and so on, and get a homogenized temperature and composition of the steel before it going for the casting. The reason why I'm saying homogenized temperature composition is that during the ladle refining process, they try to add some kind of alloys to meet the required chemistry. You might have seen different types of steel, right? Carbon steel or stainless steels. So all these different type of steels have a different chemistry and different properties. And all the chemistry and properties basically differ at the ladle refining process. So if you can able to meet the required chemistry and the required temperature, And
Ma'am.
that is there anything anyone asking?
No, sir. No, sir. That is a nice pet.
Okay. So that is the place where we can able to get a very good quality of the steel that is coming out of the casting process. So now, as I introduced my, the problem statement, and we may ask, can we do this kind of trials in the plant or laboratory? The answer is no. The reason here is that the ladle volume is around 200 metric tons and at 1800 plus degrees centigrade temperature. So if you want to do any laboratory experiment, it's very tough to estimate it. Also, and if you want to do the same trials in the plant, and if you have not succeeded, then entire 200 metric ton volume was getting wasted, and we need to supply much more energy to remove or to make the required chemistries. So this is one of the challenge for the basically the steel industries. Now I think they might have improved the process, but you can see a lot of articles are publishing in terms of making a golden batch, I can say, for meeting the required chemistry. So there are a lot of literatures are happening, and a lot of publications are also coming on the ladle refining process itself. If you get some time, just look at the research that is happening around the ladle refining process. And if you see in the bottom picture, this is a typical chemistry that is happening. And within the ladle refining, it's a multi-phase phenomena. Basically, so the steel is at the bottom, and the top there is called as a slag. Basically, that slag is another material having other density and which cannot dissolve in the steel. It always float based on the density difference. The advantage having a slag at the top is to minimize the radiation loss from the steel to the atmosphere, because the top lid of the ladle refining is open to the atmosphere and the steel is at 800 degrees centigrade, 800 degrees Kelvin of the temperature, operating temperature. So, and we always know that the temperature difference is very huge and there could be radiation losses. That if you use more amount of energy from the steel, then steel starts solidifying within the ladle and that cannot go down. So we need to stop the process and we need to use mechanical operators to remove the steel from the ladle refining process. So that is the major advantage of having a slag to control the heat. And other phase is the argon, which I have not displayed here. So there was argon or inert gas were purged from the bottom. Some industry may have sides, but most of the industry will have at the bottom. So the bottom injection will help to maintain the circulations. To create the circulations within the ladle refining process to have a very good homogeneity of the temperature and compositions with respect to time. And these three are the phases. As I said, steel, slag, and gas. There are three phases. And when we have a circulations, what happens typically is that the mechanical part of the ladle refractory, we call it as, so that sometimes that is going to be breakdown and it will come into the steel. And this mechanical inclusion, we call it as inclusions. This inclusion has to be removed before it go for the next unit operations. So this can be removed. Basically, this is a kind of solid particles, and these solid particles typically with the what typical how it was happening, and this will also have lesser density, and this particle can float to the upward direction due to its drag force or rotation velocities that they have if the steel is at rest. But if we have some kind of rotations within the radial refining process, so this particle may stay within the steel or this particle may go to the slag. And the flotation velocity will depending upon the particle's shape. We call this a shape factor. So what they do is that they try to add some kind of uh, shape treatment by adding calcium injection to the system. So when we add a calcium to the system, then any kind of shape will be converted into circle or sphere, and the sphere can be easily floated to the top direction and can be removed at the slag. And apart from this, if the steel has some kind of oxygen and sulfur, and by adding by adding some chemistry such as alumina and silica that may react with oxygen and forms Al2O3 inclusions, or if you have a calcium oxide in the slag, that may react with sulfur in the steel, forms calcium sulfide and it stays at the steel. So there is a lot of chemistry that is happening, and the chemistry kinetics itself is challenging for the any kind of radar refining process, and they are not sure which chemistry that is happening, and their kinetics also another challenges that they have. And apart from that, there is another challenge will be when we have a purging here, we could expect that the slag can have opening end, which means that the steel can also have exposed to the atmosphere. So there will be losses of the temperature because eye opening at the top due to the bottom purging. So if we have exposed, then there will be a heat loss from the eye open area to the atmosphere, and also there could be a chance to absorb some amount of oxygen from the atmosphere to the steel. So if you look at it, it's like kind of more complicated, and identifying the right chemistry that is and right kinetics or right reactions happening within the steel slag reactions, it's very challenging basically. So how we resolve this problem is that we try to break down entire problem into three different sections, such as chemistries, which we solve typically the kinetics of the reactions, and also I try to identify
அட்டண்டன்ஸ் பார்த்து சர்டிஃபிகேட் கொடுப்பாங்க.
and try to identify the amount of air or oxygen and nitrogen picked up by the steel from the atmosphere. So that is like another challenge to estimate it. And temperature is like kind of typical. We already know the temperature is like homogeneity temperature. There could be losses from the side walls, or bottom wall, or top wall, and there could be losses during the purging because when we homogenize the steel with the help of argon, there could be heat loss from the argon. I mean, steel to the argon, which goes to the topward directions. And when we add additions, there could be heat loss because when we add, it's at the room temperature, and there could be sensible heat that is transferring from one side to other phase. And I mean, when they add here, one point is that when they add the alloys here, or when they do purging here, and the temperature of the steel is getting dropped out, and if you drop much more than the melting point or freezing point, then steel starts solidifying within the ladle. So to control the temperature, what they do is that they supply heat in the form of arcing system occasionally during the ladle refining process. So that is one of the physics that we need to consider during the simulations. And third physics is the inclusions, which is the unwanted solid particles that is forming during the process, and how does that will be separated from the steel using a different physics that is happening within the system. So it could be collision between them. When the two inclusions collide each other, it may break, or it may form a new bigger size particles. When it break, and how does particle is moving? Is it moving to the top direction, or is it moving side direction, or is it moving bottom direction? When it moving the top, whether slag is having very good absorbability to absorb the inclusions that is coming to the slag surface, or when it is going to the wall, is it attached to the wall, or is pushing back towards the steel? So those kind of kinetics has been simulated within the system to understand final inclusions chemistry that is happening, that will be there at the end of the laboratory process. So let's look at kind of detail in terms of process. And as I said, ladle is a batch process typically. And here if you see the chemistry, as I said previously, there are multiple chemistries that is happening within this ladle refining. But ladle is a batch process. And how does it ladle cycle look like? Basically, let's say if you're using a fresh ladle, which is a new ladle line, what they do is that they try to heat the ladle before it receive the 1800 degrees centigrade or 1800 Kelvin temperature of the steel melt. They try to preheat around 1000 degrees Kelvin, and then it go for the tapping of the steel from the basic oxygen furnace, and they do treatment. Once the treatment is done, it's going for the casting, and casting for the solidifications. Once it's empty, then it's go for again preparations, because during the refining process there could be removal of some refractories from the wall of the ladle refining to the steel refining process. So they try to refix it and get a proper align of the refractory lines, then again go for the preheating it. So it's kind of a cycle, and when we try to identify or control the temperature, it's always dependent on the each individual operations. For example, you preheated up to 1000 degrees centigrade, but you waited for more than, let's say, 10 hours or 20 hours, the temperature always will drop out, or that will reflect on the temperature of the system. That means we may supply more and more, we may need to supply more amount of heat, or vice versa. So such kind of things needs to be solved using simulations, because it's easy to understand, but when we simulate it, you'll able to see the very good understanding of the process and how the profile of the temperature or chemistry happening in the system. So because when you measure it, you will measure it only one location. You cannot measure it within the entire system, right? But when you simulate it, you can always see at with respect to space, what is the temperature and what is the chemistry and what is other inclusive composition or whatever it will be. So that will be very good. That information will be very good to control the process. So modeling along with the technology that they have in the plant team will combine together, will help us to understand much more in detail if we need to minimize basically the dead zones. Typically we call this dead zones in the CST reactor, right? So this is kind of CST reactor we can talk it about, but it's a batch reactor with having purging, and which also has some kind of dead zones at the side corners when we have a purging at the bottom, right? So there could be chance. So that kind of analysis can be seen where are the dead zones or hotspots were present, and how do we eliminate them before it goes to the next one operations. Is it clear?
Yes, sir.
Thank you, sir. Then let's see. Basically, the chemistries, as I said, the chemistries are unknown factor, and it's very tough us to get right kinetics of the individual operation. Individual process or reactions within the steel slag reactions, because it's always depending upon the kind of steel chemistry, slag chemistry, and operational conditions that happening. But there are ways to approach or calculate the chemistries based on the data available in the plant or on the literature data. So here what I have done is that I try to use the available data from the literature, because we did not get a plant data directly initially. So we try to use available data in the literature and try to formulate kinetics of the each process, and also we have considered the thermodynamic calculations to estimate the extension of the reactions of each product. Okay, so for example, if you see the CAS plus sulfur forms calcium sulfate plus oxygen. So here bracket indicates from steel side and open bracket indicates from slag side. So just to give a notation. So when there is a reaction between slag and steel, it could form. So based on thermodynamics, we can able to see what is the extent of formation of these reactions. And once it formed, then we can able to calculate the kinetic of this formation reactions using the data that we have in the literature data. So that's how we solve here, and there are two different, not two, so multiple different ways to estimate the basicity, which is a very important factor for slag chemistry, because when there is a sulfur or composition of slag was changed, the slag itself is getting changed in terms of the physical systems. So one is called optical basicity or sulfur capacity or sulfur ratio. That will determine whether sulfur is getting reacted with the slag and forms sulfur dioxide or not, along with the kinetics what we have. Because these are calculations based on the thermodynamics, which are Gibbs free energy minimization or chemical potential minimization methods. But these measurement will help us to understand, is it really happening or not. Once it really happening, then we can use kind of correlation to estimate the kinetics of it. And similarly, we know the oxygen, if there is an oxygen and there is a element is there, agent is there, definitely oxygen will try to react with the oxidation agent and forms its formula Al2O3. So there is always, because all oxygen has very high tendency to form and remove from the steel at the given temperature. So it's not needed to have kinetics of it because it's have very good high potential to form. So that's why we don't have any kinetics of these reactions. But coming to the nitrogen separator, so here basically we don't have any equations, but we try to estimate the kinetic equation based on the data that we receive from the literature data, experimental data or literature data or published data. Similarly for hydrogen, and for the purging, picking up the oxygen and nitrogen from the atmosphere during the process. Again, we don't have any kinetic equations. But we have a literature data. How much of oxygen has been picked up or nitrogen has been picked up based on the kinetic or thermodynamics of the steel and oxygen absorbance. So then we derived these equations based on the data what we have. And these may or may not valid for any kind of systems, but this will valid for at least, will understand, it will give you at least some background or quality way of measuring the oxygen pickup or nitrogen pickup or any kind of kinetic equations in addressing how the system is behaving with respect to the time during the ladle refining process. Let's
Once
leave. And as I said, the slag is like, as I said previously, the slag is used to control the temperature. It's also used to absorb the inclusions. And there are two different properties of the slag that they were measuring to say whether currently slag is good or do we need to add any slag material to control the to remove more inclusions or to control the temperature drop within the steel based on the two different properties such as the slag basicity and also slag fluidity. These are directly taken from the literature equations, so it's not developed by us, it's already available in the literature. So these two are the major parameter, and basically in the steel industries, what code they have is that if you try to control the slag will automatically control your ladle refining process. So that is the basic slogan that they have. So most of the time they try to control the slag during the operations so that at the end of the ladle refining you will be able to see very good steel that is coming out of the after the process. Now, so you have seen the kind of equations that we used, and once we have those equations, those kinetic equations, we started developing a CFD-based model to understand the chemistry of the system. And you can see, and this paper was already published in the literature. And here, if you see, we solve all kind of CFD equations, which are the momentum equations and mass conservation equations and turbulence equations, and also it's a multi-phase, so we have used volume of the fluid. It does not require to have solved Euler-Euler models. Just it's okay to use to volume of the fluid models. Once we have this velocity information, then we passed it to the kinetic informations, and we also pull the thermodynamic calculuses from the thermodynamics to identify the extent of the reactions. And we have used various kind of kinetic equations which I have shown in the previous slide. And this is kind of integrated model that was developed because thermocalc is a different software. This block is a different coding knowledge, and this is a CFD software. So there are three softwares integrated together to estimate it. And if you see figure 2 or the validation, so fig A will be the literature data and B is the simulated data what we have, and you can see it's pretty well matched with respect to the flow directions. And also if you see in the bottom left hand picture, this is how does the percentage of sulfur is decreasing with respect to time, process time during the ladle refining process, and comparing with respect to the simulation data versus the CFD coupled data. You can see as reported reported literature, the sulfur content is continuously decreasing with respect to time, and that can be similarly we can see the same thing, but there is a little difference in our calculation versus the reported values. that could be explained by using the kinetic equation that we have used. Because as I said in the starting, whatever we used kinetic equation may not valid for entire range of the steel industries, but at least it will give you the trend directions. So with this validation, we started identifying what could be the argon purging rate that we need to operate so that we can able to have lower sulfur content at the end of the refining process. You can see if you go beyond 300 normal liter per minute, it always the same. You cannot reduce much more than that. So that means this is the equilibrium point. You cannot go beyond that. So with this information, we can able to say that okay, minimum 300 NLM we need to use to remove maximum of the sulfur content from the systems. So once we develop this CFD based model, and also we try to develop, we did various kind of series of simulations to correlate, because if you want to do a discrete twin oriented simulations, we cannot always connect the CFD simulation, because CFD simulation will take a longer time. That you have a multi-phase simulations and transient simulation. It takes ages time to get the response. So what we did is that we tried to develop rigorous equations to estimate how does chemistry of the steel or slag will be at the when we change the different kind of slag compositions. So we did these calculations externally before we connecting to the discrete applications, and we arrived two different types of equations, and we got validated them using the actual calculations was the versus the calculated based on these two equations. You can see most of them are pretty well matched. There could be some deviations at somewhere, but the deviations can be acceptable because the percentage of deviation is very less compared to the acceptance levels. And here we used basically linear equations and also non-linear equations, but we used only the linear least square minimization method to estimate the coefficients such as A0 to the AN. So how I have resolved this equation, I hope I'll explain in the next section tomorrow. How we can resolve, how we can able to solve these linear equations using least square method, much more detail in the next sections. Coming to the steel, once we chemistry is completed, we started simulating the temperature. And if you look at the ladle, empty ladle itself, you can see there are different kind of lining system that will be there. It started with the metal, then started with the various kind of level of what you call refractor was placed here, and that the outlet will be metal shell. So it's not completely stainless steel material or any kind of metal oil vessels. Initially it will have some kind of refractories followed by the metals. And we have basically we have a temperature measured at the ladle outlet at the surfaces, and also some temperatures. Occasionally they pull some temperature at the during the process. So what we did is that we tried to simulate them and validate them temperature and compare with the measured value versus the simulated values. And if you're not able to meet the measured values through the simulation, what we did is that we try to change the heat transfer kinetics, such as overall heat transfer coefficient. So we try to manipulate that to match the temperature of the ladle refining process. And once we got a very good heat transfer coefficient, which represents the heat transfer of the ladle refining heat transfer from the steel to the other areas, then we validated that model for almost 90 different set of data. So you can see most of the place it was pretty good validated this for the temperatures. So once we have estimated the kinetics based on the tuning of the overall heat transfer coefficient, we started simulating physics of the heat transfer for all kind of sections or all kind of physics that I have highlighted in the previous slide. So we started with radiation losses in the top direction or axial directions, heat losses by simple natural convections or conductions or convections, and also when we add a purging, so how much of heat can be lost And when we have addition, how much of heat can be lost due to the additions, and when we teaming it or pouring to the steel, how much of heat loss can be. That heat loss can be used, calculated based on the Stephen's law, that is radiation equations. So here, all the temperature equations we solve through the simple auxiliary transient equations, and the kinetics of the equations are calculated based on the data that we have. So we solve the temperature, chemistry, and now we are trying to see the inclusions part. So when the steel, when the inclusions were formed during the refining process, you see the velocity. First figure, right as the top picture is velocity profile when we have a different purging systems. A will be at the center purging, B will be off center purging, and C will be when we have a two off center purgings. How that velocity profile look like. These designs are very important. Important for one, controlling the temperature, controlling the chemistry, and also to control the inclusions. So that can be explained here. So here, if you see, we solve with the two different phases because we assume that once it reaches to that top layer, it was absorbed with inclusions. Slag interface. So that's why they just solve within the steel and argon purging. That is very good approximations to estimate the inclusion behavior within the steel process itself. And there are basically solved. This block was solved using the CFD software, and also on top of it, we have written some kind of scalar transport equations to estimate the number of inclusions and also chemistry of the composition of the inclusions within the ladder refining process with this time. And this was solved using some our ODFs. Now you can see the bottom three pictures on the right hand side. So each design we have their different level of inclusion index. This and index are the inclusion number. So you can see lower the blue have a lower the inclusions, higher the red have higher the inclusions. Okay, so this can be, by looking at the CF results, we may not able to get much more clear idea which design is better, but we just plotted the inclusion density for particular particle size for three different designs. You can see dashed line is a type A, which is in the here center purging, and continuous curve is type B, and dotted curve is type C. So moreover, type C and type B are giving almost same response to have lower inclusion density with respect to time. That means that if we having either off center or the two plugs are giving much more efficiency to remove inclusions, and if that can be seen in any of the graphs. So the physics that we have used in the scalar transport equations are given here, and the kinetics of them, basically this 1.3 and 2, 3 are taken in the from the literature. So there is no data science or included here. Most of the data science are included in the estimates of the kinetics, chemistry, and also the therm and also the heat transfer coefficients. So now all the three models were developed and combined together to calculate for given conditions what could be my temperature at the end of the process, what could be my chemistry at the end of the refractory process, and what could be my inclusion at the end of the process. And so once we have set of series of data, then we try to recorrelate them in terms of reduced order models, because these are very useful to connect with the digital twin or to use optimization. For example, if I want to identify optimal conditions, we cannot always call CFD simulations to run the particular set of iteration, right? So because simulation itself is going to take a lot of time. So what we did is that we tried to correlate. We did a series of simulations, and using that series of data, then we correlated back using our linear equation least square method, minimization method, to correlate all the variables for temperature and also the inclusion density. And the cost I have defined based on the amount of arcing that we have used, amount of addition that we have used, and how much time that we have used parsing. So that factor were included here to estimate the cost, because when we see any kind of operation, they typically see to minimize their operating costs. So if you can able to minimize operating costs and get the maximum yield, that will be a very good golden batch. So that's why we have taken the cost also another estimation of the correlations. And these correlations were validated with a detailed model for the 4 different cases. You can see most of them are pretty well matched, except this zone where I have a difference of around 0.5 between absolute number of 0.5 between response surface models versus the detailed model. So here we have used again data analytics or data science approach to correlate it, because it's a least square method minimization, it's a linear regression models. And now we have, before we move on to the next slide, is there any questions? Is it clear?
Yes, sir, it's so far clear, but the participants may be asking at the end of the talk.
Okay, thanks. Okay. So this is very good, interesting. Another key element. So we have developed regressive equations. Now using these regressive equations, we try to estimate optimal conditions to get a very good process conditions to meet the required golden batch of the ladder defined process. And when we say optimization, we typically try to see the solution like this. That means that the optimal solution is the virtue of the maximum point or minimum point. Okay. For example, we are at the maximum point, right? And none of the plants will work at the maximum point. The reason behind here is that it's very tough to maintain a constant temperature when we have a controlled temperature. For example, you have a temperature of the reactor is like 500 degrees centigrade. And you set a control temperature at the 500 degrees centigrade. But operation may not have a 500. It will always have some perturbations to the set point. Maybe at 495 or maybe at 505. There could be plus or minus of 3 sigma level of the range. That means that if I have 500 and my operational is 505, that means that the optimal point will either fall down drastically, either right hand side or left hand side, based on the operational conditions. So if that is the case, this is not the right solutions, because we never operate up exactly the same point with respect to time all the times. So here the idea is that not to identify peak point, but try to identify a flag point where I can try to maintain at least 3 sigma level of the variation, so that my system will behave stable during this 3 sigma level of the variations. In this situation, my system is not going to behave stable, because when we change 1 sigma or 2 sigma, 3 sigma, sigma is a standard deviation of the dead signal. So the system drastically drop out from the point. But here it cannot, because we have a flat surface solutions. And let's look at how the response look like. And this is like a control factor, a noisy factor, and response. And f is a function. And this is the plotted function of x with respect to the design error. And this is the curve that we receive. Okay. And if you try to look at any optimization, conventional optimization that we have, we try to predict the global minima, which is this point. And if you identify, if you try to change any kind of small deviation, you will get this kind of very huge deviation in the output response. You can see if you plot here, right? And if you go towards the other robust solutions, where you can see here, there is a huge flat. But if you give the same variation in the x variable, the deviation in the y variable will be very small. Okay. So similarly, if you plot a minimum or maximum point of the response surface, and if you try to plot the deviation from the minimum and maximum for a given ranges of variation of the x variable, you can see that there is a huge deviation in the y response between the minimum and maximum. Similarly, if you look at this solution, Even the previously we have a small point, but the difference between the min and max line will be huge. So neither solution 1 or 2 are not the right solutions, but the solution 3 where this we have deviation or difference between the min and max are small, and also the response solution, absolute response solution also very small. So third solution will be a robust solution where we have deviation is smaller. So the algorithm right now here we have used this to identify the robust solution, which is a type 3 here, is based on the CDSP, which is called as compromised decision support problem. And it was developed by Professor Mestri and Allen from Oklahoma University, USA. So here, basically in the previous, any typical optimization problem, what we do is that we try to solve basically f of x equal to 0 and identify minimum point or maximum point of f of function by subjected to constraint maybe gx and gy. So that's typical standard approach to solve optimization functions. But here, when we talk about when we have multi-objective functions, it could be the same. We may use multi-objective functions, but in the CDSP problem, it's not. We are not solving the absolute functions, but we are solving the deviation functions, and the deviation functions are called calculated based on the deviation variables. So that those are called as di minus and di plus. And di plus or di minus were calculated based on the targeted value minus the current value. So that these are my deviation variable. So that was re-estimated, and that was used as objective functions to estimate the solutions. And now we have seen the methodology of the optimization functions, and we have seen the equations, and we have used that equation, and we try to resolve the problem for identifying the right optimal regime to have golden batch productions. And this is a typical ternary diagram. I hope you might have remembered our ternary diagrams, but it's similar to that. One variable will be the weight of the sulfur content, other variable will be efficiency, which is inclusion removal, other variable will be the cost functions. Okay, so we try to use these three as objective functions and try to plot identify the operational regime to get golden batch of the ladder effect. And here the condition, for example, I want to have the cost is less than 0.5. Okay, and you just plot cost curve within the ternary diagram. You could be able to see this is the curve that you could be able to see, and the below this curve will be a better regime which can give you the cost is less than 0.5. And if I want to have sulfur content is less than 0.3, and you just plot wherever the sulfur is less than 0.3 on the ternary diagram, and this blue zone is the one where we have less than 0.3 of the sulfur. And if we plot efficiency more than 80%, and if you plot that line on the ternary diagram, this will be my zone where I have efficiency is 0.8, more than 0.8. Now, if you look at here, if my objective is only on the cost, and this is the regime, I won't bother about what would be my efficiency or what would be my sulfur content. And if you're looking only in the terms of cost, minimizing the cost, you can be able to pick any point within this regime. Or if you're looking in terms of sulfur, I want to minimize the sulfur content in the ladle, whatever it cost may be, whatever inclusion may be, then you can able to operate ladle refine in this region. And if you want, your aim is to look at only the inclusion efficiency, removal efficiency, and I don't bother about cost or sulfur content, then this will be an operating regime. But when we talk about all the three objectives together, I want to have minimum cost, I want to maximize the sulfur content, removal, I want to maximize the efficiency of the inclusions. Then we need to plot all the three zones into single, and you can see there is no common zone between all the three sections, because to get there will be a common zone for two sections. For example, for if you're having a combination of cost and sulfur content, you have a common zone at here. and you have a common zone at here, but nowhere inclusion were included because inclusion zone will be at these locations. And if you have a common zone between sulfur and inclusions, this zone will be a better operating regime zone. So plant can operate at this. So previously we have seen individual objective functions. In this plot, you can see two objective functions at a time. We are interested in cost and sulfur content. There will be two zones are available. We are interested in efficiency and sulfur content. Again, single zone is available. But if we are interested in efficiency and cost, there is no common zone is available. But if you want to have all the three zones together with this limit that we specified, is nowhere possible. Then what we did is that we tried to eliminate or modify the required conditions from 50% of cost or reduction normalized value to 85%. So I'm okay. I can, because I don't want to reduce my current cost to 50%. I'm okay to at least reduce 15% and have 85% spent on my target cost. So if I change my condition, then you can able to see a common zone operating regime where my ladder can perform refining can be done to get a very good ladle refining at lower cost, lower sulfur, and higher inclusion, lower inclusion content in the stream. So with this kind of basically this was developed by some of my colleagues in TCS for digital twin oriented applications to understand how the chemistry look like with respect to time, how the arcing is done with respect to time, and also continuously data was pulled from the data from the historian and try to integrate that GUI to perform forward direction or the control model. For example, you have a complete set of log series given, and if you want to see when to arc, when to add addition, that can be done using a control model. Or if you don't want to use a control model, we just give and see with respect to time how does the chemistry is evolving or temperature is changing with respect to time. That's all for today's call. This is what we developed for steel refining industries. So here we can see three different complicated models, and kinetics of them are not available, and we try to use literature data to estimate the kinetics, and we also used simulated data to convert model results into the rigorous equations using ML algorithms. And we have also seen how does those rigorous equations has been used to identify optimal regime to produce very good clean steel out of the ladle refining process. With this, I will stop for my presentation, and I'm open for the questionnaires. I hope this gave you at least little understanding how people are or industry are looking in terms of application of digital twins or data analytics techniques to improve their quality of the product that is coming out.
Yes, sir. The participants, now the session is open for the question and answers. You can raise your questions through the chat box so that I can share it to the sir. Dear participants, you can raise the questions. Sir, I think you can see the chat box. Can you?
Yeah, I can see the chat box. Yes.
So there is only one response from Ms. Nandini. So thank you, sir. Sir, I think maybe the end of your next session, they are going to ask combined questions from this talk and the next talk. Well,
Okay.
hope.
Yeah, you can ask not only this, I mean, it's not that you need to understand steel and you need to ask for the steel related questions, but you can ask anything related to analyticals or what models that I have used in terms of CFDs, how to solve the CFD problems, how to write the codes, or if you, I mean, any kind of stuff that you want to ask, you can ask. I'll try to answer them. They can able to answer.
So we are getting good responses, sir. Thank you, sir, for a very good session from
Okay.
participants. Yeah. So I hope there are no further questions. Okay. So at the outset, I would like to thank Mr. Ravikiran for his excellent speech on digital twinning process. Participants, you can type your question in the chat box if you are unable to unmute. So I think they must be texting. So we'll wait for some time. So.
Yeah, okay, no problem.
Participant Anita Muglicherla, you can type your question through the chat box. Yeah, Dr. Anita, please go ahead. Yeah, so the question is from Dr. Anita. Did you write your own code for CFD solving or any softwares used?
Okay. So for solving CFD problem, we have used ANSYS CFD software. Sometimes we use Fluent. Some problem we have used CFX. But apart from ANSYS, we wrote UDFs to solve user-defined functions such as auxiliary equations or the scalar transport equations. Typically, scalar transport equations and source terms for the scalar transport equations may not be available in the ANSYS CFD. So we have to write those UDFs into program UDF functions, basically the C Fortran, Fortran program.
Check with
So
Anisha.
address real physics. So answer is that we use both, combination of both, to solve our physics problem.
Sir, I think there are no further questions. I think Dr. Anita sir has explained your question. Yeah, so I got a response, sir. So it's okay, sir. So if there are no further questions, I would like to thank Mr. Ravi Kiran for his talk on digital twin application for steel refining process, modeling and optimization. So through his talk, he has enlightened us with his views on the breadth of digital twinning process and secondary steel making process and challenges in casting and ladle refining operation processes. And also he has explained us very neatly about CFD modeling of ladle process. And also he has neatly elaborated on the chemistry validation of ladle process and also temperature tracking method for ladle process modeling, as well as how to use the compromise decision support problem for understanding the ladle process. And at the end, he has clearly explained as the mathematical modeling of ladle process and optimization. So it was a very inspiring and a very excellent session on this particular topic, sir. Thank you very much, very much, sir. And I would like to bring to your notice that majority of the participants are from the CSC and IT, so they might be getting enough idea on this process and the talk, and they'll be asking many questions in your next session, sir. So thank you very much, sir. So for this excellent session on the topic, sir.
Thank you so much, Dr. Ramakrishna, for giving me this opportunity to provide the ideas that I have or develop idea for steel refining side. And also thank you for Sayana basically. So I just want to thanks for also to invite me or include me in the the sections. So next section I try to cover at least how to do least square method minimizations and try to have some kind of hands-on calculations at least so that I can cover at least time. Now it's within 1 hour time I have completed. So,
no issues, sir. No issues, sir. So thank you very much,
I'm
sir.
open for more discussions because people might have. I feel that they are from chemical or mechanical industries.
So they are from, some of them are from chemical and mechanical engineering, sir. And mostly this is an emerging area. So CSC and IT faculty have registered, sir.
Okay. Okay.
So from the next talk, as you are going to explain as the predicting right feed mix to control the product quality based predictive analytics. So there people might be asking many questions on that, sir.
Okay. So during that call, I think I thought to take couple of at least half an hour to 1 hour time to have least square minimization method reductions and have some hands-on calculations.
Sir.
And I'll explain the example how that method has been used to estimate real industry problems.
Sir. Yeah.
Okay.
Thank you very much, sir.
Thank you so much for giving this opportunity. See you tomorrow morning, sir.
Yeah, thank you, sir. Dear participants, the next session is at 2 o'clock in the afternoon. So will be by Dr. Alka Kumari, scientist, CSIR, IICT, Hyderabad, on the topic process design and simulation, fundamentals and techniques. We hope to meet you at 2 o'clock. So please join us before 2 o'clock so that I will start the session without any delay. Thank you. Thank you all.
Good afternoon, everyone. The event will start in around 5 minutes. Our guest speaker is facing a network issue, so it will take 5 minutes. Thank you. A very good afternoon to one and all present here. I take this opportunity to welcome you all to today's session of Process Design and Simulation Fundamentals and Techniques, organized by the Department of Chemical Engineering, MVJ College of Engineering, under AICTE sponsored Atal FDP scheme. Now, I take this privilege of welcoming our today's guest speaker, Dr. Alka Kumari. Dr. Alka Kumari obtained her BTech degree in chemical engineering from BIT Sindri, Jharkhand in 2012 with an excellent academic performance. She started her career as a trainee scientist in chemical engineering division at CSIR Indian Institute of Chemical Technology, Hyderabad in 2012. During her tenure as a trainee scientist, she completed her MTech in Process Engineering Sciences from Academy of Scientific and Industrial Research, IICT Hyderabad, and worked on the process development activities, followed by completion of a PhD in 2020. She is presently working in Process Engineering and Technology Transfer Department of CSIR IICT. Her key research interest involves the process development, scale-up studies, and design of commercial plants, intensified separation techniques, estimation of thermodynamic and transport properties, and its modeling for industrially important streams, and thermochemical conversion of biomass to value-added products. Dr. Alka has been awarded the Young Scientist Award 2017 by Telangana Academy of Sciences Hyderabad and CSIR IICT Women Scientist Award 2019 and Young Engineer of the Year Award 2020 by the Institute of Engineers India and Government of Telangana. As a part of the process development and design team, she also received the CSIR Technology Award 2018 from Union Minister Dr. Harshvardhan. She has published around 23 papers in reputed international journals and presented her contributions in several national and international conferences, besides guiding 6 MTech and 10 BTech dissertations. She has been elected as the associate member of the Indian Institute of Engineers in 2016 and a life member of IICHE. We are very pleased to have you here with us, ma'am. We request you to kindly share your knowledge with all of us. Thank you.
Yeah, thank you, Manasa, for a very nice introduction of me. Yeah, so good afternoon, everyone. So first of all, I'll share my slides. Good afternoon, everyone. Can you see my slide here?
Yes, ma'am, it's visible, ma'am.
Yeah. So, good afternoon, everyone. As already Mansa has introduced me, I am Dr. Alka Kumari, working as a scientist in Process Engineering and Technology Transfer Department, CSIR, Indian Institute of Chemical Technology, Hyderabad. So, today's topic of my presentation is on process design and simulation, where I will go through the steps involved in the process design and will discuss some fundamentals of the Aspen simulation models with some case studies. So I hope at the end of the session, you will get benefited out of it and you will have some idea about this topic. So I will start with the So I will start with the process design. So process design starts from problem statement and development of its understanding for the important underlying physical sciences relevant to the problem and their use of understanding to create a plan of action. And with that plan of action, we set a detailed specification which will lead to the desired outcome. So there are different steps involved in the process design. We start with the defining of problem first. So in general, this process design step is adopted by any kind of engineering streams. So first of all, we define the problem. So where we ask different questions like what is the problem that need to be solved, and who is the design and who is the person for whom we are designing the product for, and why it is important to find the solution and what are its limitations and requirements. And once the problem has been defined, then a good designer brainstorm the problem and its possible solution. We build as many as solution possible solutions, and it is best to have all the ideas flow. We should not judge any ideas at this stage. And then next step is to do the R&D of this. Like previous literature reported, we go through the previous literature reported and earlier experience we will implement here to select the best ideas. And then we establish the criteria and constraint. Like in some cases, if we go for the process design, the economics should be viable. It should not go to the higher critical process conditions. So those constraint and criteria we will decide here, and based on that we consider for the alternative solutions. Once we establish the criteria and constraint, by brainstorming and R&D, the many design will be neglected there, and then we will consider for the alternative solutions there, and based on alternative solutions we will decide the best possible approach, and based on the possible approach we develop a design proposal. Based on the design proposal we make a prototype. We test that prototype and evaluate it consistency or the desired outcome approach. Well, if the desired approach is fulfilled, then the design is tested and approved. If not, then we refine the design and create the new solutions, and finally we document these results, and we share the knowledge either through documentation, presentations, or any report formation. So this is the overall design process any engineering stream can adopt. And especially for chemical manufacturing process plant, there is a slight deviations in the process design procedure adoption, where we will start with the project specification, like similar like problem statement we define, and initially we evaluate the different possibilities, and then we based on initial evaluation we select the process and we draw the process flow diagram, and then we do the material and energy balance. Based on material and energy balance and the developed process, we select the equipments and we design the process. So here in chemical manufacturing process, there are two broad phases are defined. Like in phase one, we do the process design, and phase two, detailed mechanical design comes. So in phase 1 process design, which start from selecting the process to the flow sheeting, and we also do the engineering design of the equipment. So generally it is done by the process design group, and the main role play here by chemical engineers, and also the piping and instrumentation diagram is done by the chemical engineers. So phase 1 here starts from project specification to piping and instrumentation diagram. This portion of the work is done by basically the chemical engineers. And then in phase 2, once the PNID diagram is done, we go for the detailed engineering diagram. So from this portion to this down portion, this is the comes into phase 2, where detailed process design involves the heat exchanger design, vessel design, civil works, then utility streams, and everything comes under phase 2. So this is done by the mechanical design group, and also the other stream engineers involved for the civil lines and utility lines. So to better understand the process design procedure, I would like to present a case study. Actually, it is a industrial project sponsored by a Hyderabad-based company. They approached us for preparation of 1 ton of furfural alcohol and 2 furic acid. So earlier they used to make furfural aldehyde from biomass source, corn cob, and they wanted us to go for the forward integration of the product, that is furfural aldehyde. So they said that furfural alcohol and 2 furic acid have good market value. So they wanted us to develop a process over that. So for that process design, we have started with the problem statement. So problem statement, as industry have already approached us for making 1 ton of furfural alcohol and 2 furic acid per day basis. So the problem is defined here. So now our work start here as a process design. So initially we brainstorm this problem, like how to produce 1 ton of 1 ton per day of furfural alcohols, like different literature reported process we see, and basic RN based on the selected process, if it is based or not. Based on the selected process, we do the basic R&D, like in bench scale process development we do, and basic raw material calculations we do, and we also look into the thing like the process conditions like temperature, pressure, and those things should not be adverse. So it should be also economically viable. So in initial evaluation, we do all those things, and based on initial evaluation, we select a best process, and that best process we do the lab scale experimentations. Like for this furfural alcohol, we come to the conclusion that Cannizzaro reaction is the best reaction possible route for the conversion of furfural to furfural alcohol and 2 furic acid. And here one more thing we need to consider here, that they wanted furfural alcohol along with 2 furic acid. So there were some processes from furfural aldehyde which only produce this furfural alcohol. So we have to keep into the mind that the process which we are selecting should be producing furfural alcohol and 2 furic acid. So based on that, we have selected that Cannizzaro reaction is the best possible route which can produce furfural alcohol and 2 furic acid. In the different steps are involved, like first is the reaction step, where we get sodium salt of uric acid and furfural alcohol. It is in mixture form. The next step is the downstream. So how we'll get the pure product? So by extraction of furfural alcohol, and by finally vacuum distillation, we get our product. And in the second step, the sodium salt of uric acid, we have to go for the acidification, and then finally for crystallization for getting the pure product. So this is the basic process selection and development steps. Once the process is developed and through analysis we have confirmed that our product formation is there what we are expecting, then we'll go for the material and energy balance, and then we go for the preliminary process flow diagram, process equipment selection and design we go, and then finally we select the instrument based on the process condition, then piping and instrumentation diagram we do, and finally a basic design report we form. So for this, for Fral alcohol, this is the overall material balance diagram shows like means it is start with all the unit operation involved in the process. Like we started with the reactor, like for 1 ton of for Fral alcohol, what should be the raw material quantity should be involved here. So we have specified all the quantities across, like this is the reactor unit. Then after once reaction is done, the total output material balance we do, then we go for the downstreaming process where separation will happen. So all each and every unit across we do the mass balance in the material balance diagram. So for making 1 ton of furfural alcohol, what are the raw materials required? What are in downstream process? How much is the solvent we require for the separation? All the thing across each unit we do the material balance, and there what are the assumptions we have taken, we have to mention there. Like in reaction we are thinking some excess quantity of the other reactant we have to take, so that also we need to mention there. So like that, this is the basic material balance diagram which we draw. Similarly, like material balance, we do the energy balance diagram. Like in here, in reactor, when while addition of NaOH, some exothermicity will be there. So to capture the heat, we have to provide the cooling to the reactor. So how much is the required quantity and how much we are giving input to that reactor, we have to do the balancing across each unit. So like material balance diagram, we have to do the energy balance diagram. So now coming to, once the material balance and energy balance diagram is done, then we do the process flow diagram. So here we have done the process flow diagram for the furfural alcohol. So what is PNID diagram? First of all, it's a basically simple drawing that uses different equipment symbols to show the primary process flow path of the unit, and it shows the major relationship between the equipments in the process plant. And it is generally used to have a quick overview of entire operating unit or the system, and also it traces the primary flow of the chemicals through the unit. And it is a code, we consider it as a core document to draw the plot data and PNID data. So from here, for furfural alcohol PFT diagram, we can say that there are many unit operations are involved, like storage tanks are there, reactors are there, stirred vessels are there, distillation units are there, separators are there. So we can get to know how many unit operations are involved for making the designated quantity of the compound, and also how the flow of the chemical is taking place. Like here we start with the aldehyde. So aldehyde, this is the aldehyde storage tank. So this is going to the reactor, and in alkaline slurry is by gravity is being added to the reactor. So here water is there. So water we are sending it to this stir vessel, and NOH through hopper we are adding to that. So here we are making the alkaline slurry by gravity we are adding into the reactor. Once the reaction is done, we are sending it to separator, where the two liquid phase is being separated, and then we are adding solvent to extract the furfural alcohol. Like similarly, the flow of the chemicals or path we will understand through PFT diagram. Similarly, for 2-furic acid, again the how many unit operations are involved in this, we'll get to know from process flow diagram. So now coming after, once the process flow diagram is done, we go for the piping and instrumentation diagram. So piping and instrumentation diagram is a detailed engineering diagram which indicates the relationship between piping, process equipment, instrumentation, and control devices. Like here instrument, maybe the temperature instrument will be there, pressure instrument will be there, flow level, concentration, and different kind of instruments information we will get from here. So in piping and instrumentation diagram is a complex form of PFD. Here it is a graphical representation of process unit where each unit will be designated with a unique number. So, or various symbols used for the equipment designation, and it is used in the capital cost estimation while doing the engineering, procurement, and construction. So, and it is also being used for the plant layout, like by seeing PNID, we can identify the hazardous area, means which is the hazardous area in the plant, and also for development of piping layout. Like in sometimes in plant, we have to go for the 1 or 2 or 3 floor. So by seeing the PNID, we can say that how the plant layout should be there. We can decide over by seeing the PNID diagram, and it also gives information about the instrumentation, like each equipment. Like here if we see reactor, so in this reactor what are the instruments involved, like this is the temperature indicator, flow measurement indicators are there, like hoppers are there, like means by seeing that we can say how many instruments are involved into that. Every instrument details we will get from this, and also we'll get the pipeline heat tracing and insulation details also we will get, and utilities, what kind of utilities is being used in the process plant, we'll get the information from this piping and instrumentation diagram. So this is the for 1 ton of ethanol alcohol, and this also we while documenting this PNID diagram, different section wise we do. Like in one section we have done till extraction, and then for second section we have done till purification part. So different section we name it as a different section so that it is easier to understand that in which section what the process is happening. Like this is 300 section. Here in 300 section 2-fluoroic acid piping and instrumentation diagram is there. We can understand all the flow, instrumentation, piping, and everything we can understand from here. And this is using generally that CAD software we use to draw this piping and instrumentation diagram. So once the piping and instrumentation diagram is done, we'll go for the we will go for the basic design report. Basic design report contains a detailed engineering diagram which contains all the process description, all the instrument information, all the PFD utilities cost, then heat tracing, everything will come into the basic design report which we submitted to client. Now coming to the process simulations. So process simulation represent a process of physical or chemical transformation through mathematical model that involves the calculation of mass and energy balance coupled with either phase equilibria, trans properties, or chemical kinetics equations. So there are different engineering tool available for the process simulation. Like ChemCAD is there, ChemPro is there, Pro2 is there, Aspen Mysis, and Aspen Plus is there. So generally the process simulator is used for the automated calculations, material and energy balances, physical properties estimations, and design and rating calculations. So here in this session, I am going to talk about Aspen Plus case studies and some fundamentals about this. So Aspen Plus was initially released in 1982 by Aspen Tech, and it was the software released which is widely used in the process industries. And Aspen Plus can handle very complex processes like including multi-column separation system, chemical reactor, distillation of chemical reactive compounds, and even electrolyte solutions like mineral acids and sodium hydroxide solution. Now, recently, the polymer models are also available in Aspen Plus software. So for accurate design of any process plant or process design, we need to have the fundamental understanding of our system. So generally, any process simulator does not design the process. We should have, users should have the idea about the system, and then we input the parameters, and then based on our input parameters, the simulator will give the process performance what we have designed in the simulator. So there are different Aspen packages available, like Aspen Dynamic, Aspen Plus, Aspen Dynamic for steady state simulation, Aspen Plus is for steady state simulation, and Aspen Properties like chromatography. There are different packages available in Aspen. So I have gone through the Aspen Plus and Aspen Properties. So Aspen Properties package is available within the Aspen Plus, or even Aspen Polymer is available within the Aspen Plus. So I'll give overview about this Aspen Plus with some case study now. So this is the Aspen Plus user interface looks like. Generally, this is the flow sheet area, and this is the model library where different kind of models are available. And this is the left side shows the navigation pan where different setup configurations are there, analysis flow sheet, and the input parameters, and we can see our results and flow sheet options, everything from the left navigation key. So as I discussed earlier, this is the model library. So in Aspen, Aspen Plus, there are different unit operation model types are available, like mixer splitters are there, separators, different kinds of heat exchangers models are there, like shortcuts, and rigorous columns models are there, like different kind of reactors models are there, pressure changes, manipulators, solid simulation, solid models are available. Even user models also can be done in the Aspen Plus. And which model is going to be used for what kind of applications? There are online help menu will be there. So from that, or even in Aspen also, there is a help menu is there. There we can read this document and we can get an idea what kind of models can be used for what kind of applications. So like I said, there are different models available in mixer splitters. Three kinds of models are there. In separators, there are 5 to 6 kinds of models are available for different kinds of applications. Similarly, for the reactors also, based on equilibrium, based on mass balance, and based on rate balance, there are 7 kinds of reactor models are available. So based on our application, we can select these models for the simulation and optimization. And in heat exchanger also, there are different kinds of models are available. Many models are available in the Aspen Tech software, but Aspen Plus software. But for some models we have to take separate license for that. So in columns, shortcut, there are 2 types of columns models are there, like shortcut and rigorous. In shortcut, we have 3 kinds of models like DSTW, DSTL, and SECFRAC. And in rigorous distillation column, we have like red frac, multifrac, petrofrac, wedge frac, red frac. And in this also many have in Aspen Plus models are there, but some we have to take license separately. In solid simulations, also we have different kind of models available based on the specific applications. And in pressure changers like a vacuum pump, compressor valve, or pipe, we have different kind of models available. So one of the basic and main component and significant factor in the simulation is to select appropriate property models. Like in Aspen Plus, there are different property models are available, like ideal models are there, equation of state models are there, activity coefficient models are there, and there are special models also, that is hybrid models. So based on our system, based on process condition and degree of non-ideality, we select out of these models which is best suitable to our system. So now I'm going to present a case study regarding I will. So I'm going to explain about the two models available in SN Plus, that is DSTW model and red flag model. So DSTW is a shortcut distillation method, and it works based on the simple equations like Wien equation, Underwood, and Gleland equation. So based on Wien equation, minimum number of stages it gives, and Underwood equation solves the minimum reflux ratio, and Gleland gives the reflux ratio for a specified number of stages or vice versa. And DSTW works on the basis of constant relative volatility concept and constant molar overflow, where the system shows the non-ideal behavior. The shortcut distillation column does not work in that case. So in that type of systems, we go for the red flag, that is rigorous multi-stage separation column, where based on the vapor liquid and vapor liquid phase, we can simulate or optimize the ordinary distillation columns like absorption columns, stripping columns, azeotropic distillation, reactive distillation, and hybrid distillation systems also we can simulate using red flag distillation column. And in red flag distillation column, any kinds of any numbers of feeds or side draws we can give. Even we can give pump rounds, vacuum pump, we can connect to that. Any numbers of heaters or decanters we can connect to the red flag column. And in red flag, there is underlying physical relationship is mesh equation it solves. Mesh equations means mass and energy balance. Equilibrium means there should be equilibrium between vapor and liquid phases, and also summation of liquid phase and gaseous phase should be equal to 1. Based on that equation simulation, it can predict the stream flow rate, composition profiles, then temperature profiles, pressure profiles, operating conditions it can give us, then equipment design it can give us. So DSTW column is the design based column it says, and red flag column is a rating based column we say. So I'm going to explain a case study using DSTW column, which is a shortcut distillation model in Aspen Plus, where I'm going to separate a N-butane and cis-2-butane mixture, where our target is that 90% of N-butane and 1% of butane should come into the distillate stream. So here already, as I said, using a DSTW model, we cannot solve the highly non-ideal mixture. So like I will try to give that even example by telling that ethanol water mixture is a non-ideal and it cannot be separated by the DSTW. That in further course of the study, we will be going to do that. So as I already mentioned that DS2W column works on the basis of constant relative volatility and constant molar overflow basis. So here the example what I have taken is just for the specific concept and principle. This does not actually represent the real situation on industrial application. Just for the concept explanation, I took this example. So so in this case study, we'll start with the Aspen Plus simulation. So once we open the Aspen Plus software, we get first thing is the blank simulation template we get. So we'll open that blank simulation template, and then the left navigation pan, we have the component specification and selection. There we enter, like I said, N-butane and butane system we have selected here for the separation purpose. So we select our component in butane and butane. And once we select these two components, the component lies automatically filled into the specific places. Once we have filled our components, then we go to the methods. As I said, method should be selected in such a way that reflect the system properties actually. So in this case, we have taken the Penn Robinson as a base method and method name. These two should be the same, and this portion of petroleum calculation option, we should not touch in this study. This should be left as it is. Once we have selected our model, we'll go to the, actually the earlier two components, and the method selection we have done in properties environment. This is the property environment. And then now flow sheet environment, we will go to the simulation environment where we will draw our distillation DSTW column. So from model library, we select the tab and we can drag this DSTW column. And from material stream, we can connect this feed input and output streams. So we can rename these streams by right clicking over that. We can rename these streams by right clicking over that, and we can rewrite even. And once we are done with the flow sheeting option, we will double click on the feed stream and we will enter the input parameters. Like in feed stream pressure, we have defined here 1 bar, and in vapor fraction, as composition of the feed stream of butane, and butane is 50-50%. So we have a vapor fraction, we have taken 0.5, and in the component list, those two 50-50 we have mentioned here. Once the feed stream input parameter is done, then we'll go to the flow sheet again, and we will double click on the distillation column, DSTW column block. Now we will enter the block parameter. So once the block parameter input section opens, we enter here the reflux ratio, initial gas, something we have to give here, and then condenser and the boiler pressure we have to mention. Like in this case, we have mentioned 1 bar. And in light component, like in distillate, we wanted our pure component butane. So that we have to mention like 99% of purity we want in butane in the light fraction or top phase product. And heavy component will get in the top fraction as less than 1%. So that we will enter these details here. Once the block parameter and input parameters is done, we'll go to the simulation, we'll run the simulation, and we'll get the following results from this. So here we can see that we get the minimum reflux ratio of around 13, actual reflux ratio of 26, and minimum number of stages we got 64. So here we can say that we are also getting the condenser heat duty, the boiler heat duty. So these informations we will get, means we have designed our column. So once we are done with this, we can save our simulation as backup file or compound file. So this was as a case study for simple butane and butane mixture that was not showing any non-ideal behavior. Now we will we'll go through a So now we'll go through a complex ethanol water system which shows the non-ideal behavior. We'll try to solve this system using DSTW model. So here again we will enter our components like through component specifications, water and ethanol. And then we have selected here property method, that is unique RK method. Once the method is selected, will review our binary interaction parameters. Like all the parameters should be available for those two for the system we have selected. Once the binary parameter selection is done, then we'll go to the simulation environment and we'll draw our flow sheet and we'll connect our material streams. When the flow sheeting option is done, again the feed input parameters we will put, like again here we have mentioned pressure conditions, vapor fractions, and feed compositions like 50-50 we have mentioned here. Once the feed stream parameters is done, we'll again go to the block parameters, and again there will here we have a specified reflux ratio as a 2, condenser and the boiler pressure is 1, and light component here is, in this case, is ethanol. So that light component purity we want as a 99%, and heavy component is water, so that should be less than 1%. So that we have defined it here. So once the block parameter is done, we'll run the simulation by clicking on the next button, and we are getting here minimum reflux ratio stays minus 39, and actual stage is minus 62, and feed stages is minus 59. This is not at all possible. Negative value is not at all possible. So it shows that water ethanol form an azeotrope, and it does not follow the constant relative volatility. So DSTW U column is not able to simulate this kind of system. So for this kind of system, we'll go for the red flag column. That is more rigorous simulation model. So we have taken the red flag model. So as ethanol and water shows the azeotropic behavior. So from again model library, we select our red flag column, and the flow sheeting is done, and we connect the material streams. And one more thing, means whatever output compositions unit we want to report in SI or anything, we can select from unit set options, in which unit we want our material flow stream to be reported. So like in this case, mole fraction basis also we can select, mass fraction basis also we can select from the report option in Aspen Plus. So once the report option is done, again, we'll start with the component selection here. So we have selected our ethanol water. Now we are doing it in red flag column. So once the component selection is done, we will select the base property method. So in this case, we have selected the unique RK method for the base property method. So once the property method we have selected, we will select the, we will review our binary interaction parameter available. And then we'll go to the feed stream, and we will input the feed stream details like 25 degrees Celsius. We have taken atmospheric pressure. What is the ethanol water compositions we want, we can enter it here. And then once the feed stream input parameter is done, we'll go to the block parameters. So in block parameters, we can define number of stages, what type of condenser we want, distillate rate and boil up rate. So these two parameters, how we can input, like from where to start these two parameters. So before going for the red flag, that is regress distillation column simulation, we can through DSTW column, we can get this input parameter, even though that is not accurate, but for as a base start point, we can run the DSTW simulation column, and we can get the minimum input parameters from that simulation, and we can enter that minimum details here from like distillate rate, boil up rate, minimum number of stages. We can enter that will be considered as a starting point for the regress distillation column. Once the input parameter is done, we'll run the simulation, and we can get the throughout the column how is the means ethanol composition profile is there, how is the water composition profile is there. We'll get reboiler duty, heat duty, reflux ratio, every details we'll get out from here, and we can get in this plot term also TXY data. So this was the red flag column simulations which I have shown. So now I want to show you one more thing, like how we can design our any simulation. Means which process design is best for adopting in the real environment. So I'll take you through one case study. Yeah, you can see this slide now. Yeah, you can see the slide now.
Yes, ma'am.
Okay, so I'll take you through the one case study where different kind of process design we can evaluate, which we can adopt in the real case. Like we have taken the acetone water mixture here. So acetone water mixture, either it is feasible to separate this mixture using only distillation, or either a combination of units like extraction plus distillation. So through this case study, I'll show you which is the best method we can design through Aspen Plus simulation. So here we have taken the system water acetone. It is also a very highly non-ideal mixture, even though there is a difference in boiling point, but due to non-ideality, it shows that volatility rate of both are same. So we are taking this composition as 50% of each compound. And in this case, I'm selecting the extraction. Like I said, there are different models are available. So extraction column models are also available in Aspen Plus. So, so here solvent based on the earlier investigation, the solvent was selected as 3-methyl-hexane here. So for this simulation, the components are selected water and acetone, and the base method we have selected Unique-Vec RK method. Once the method we have selected, we will review the binary interaction parameters. And once the binary interaction parameter we have reviewed, we will go to the simulation environment. We will select the material stream. So here we can define our feed composition, feed conditions and compositions. So feed conditions like temperature and pressure we have mentioned at 25 and 1 bar. And composition of water is stone is 50 kg per hour. And we want our results to be in form of mass fraction and mole fraction. So we will tick this checkbox to get our results in this unit. Once we have selected those two components, the solvent we can select from either component list, or there is a advanced search list for the component selection. So from here we can select this compound, like solvent is 3-methyl-hexane we have selected and we have added. So now we can see that all the three components which we want to use in the simulation environment is completed here: water, acetone, and 3-methyl-hexane. So for this also, we will go to the method and we will review the binary interaction parameter. Like for water and acetone, we have already reviewed the parameters, and water and 3-methyl-hexane, we got the LLA literature binary parameters. And also acetone and 3-methyl-hexane, we should have the binary parameters. Maybe this is not available in the Aspen Plus. So that's why we selected here is the Unique-Vec property. Like I said, here base method is, we selected here a base method is Unique-Vec RK. So Unique-Vec RK method has ability to predict the unknown binary interaction parameter based on group contribution method. So these two parameters are available, and for the acetone and 3-methyl-hexane, the unknown binary parameter is estimated through Unique-Vec method, Unique-Vec RK method. So now we'll go to the main flow sheet, and we will draw our overflow sheet process design. So we have to select our from model library, we have selected the extract column where feed is entering from the top of the column and solvent is going from the bottom of the column. So here the top and bottom concept is based on that lighter and heavier component. Like solvent here, what we have selected is light density is less. So we have based on gravity, we should go. So based on the density difference, we are selecting the top and bottom feeding approach. So and in feed, it contains acetone and water, and solvent we are taking so that acetone will come into the extract phase, that is rich solvent phase, and water will remain as a raffinate, means lean phase. So again we have to separate here acetone and 3-methylhexane, that is solvent rich phase. So that we are sending it to red flag column, where we will be separate acetone and this solvent, and the solvent can be recycled back to the extract phase. So this is overall process design, which is a combination of extraction plus red flag distillation column. So for the same problem, we are going to solve a single red flag column, and we will see how based on both a strategy, we can decide which is the most efficient strategies we can adopt for the separation of acetone and water. So once we have completed our flow sheet, we will give all the input parameters like feed stream parameters already we have given, like solvent stream parameters we will define now. So solvent stream parameters, like we have given temperature and pressure, and flow rate, how much S by F ratio we want to maintain, that we can enter it here. Then we'll go to the block parameters like extraction column. These block parameters, how many stages we can start with. The initial some guess value will take, and we'll start the simulation. So number of stages is 8, and in the there are first liquid phase and second liquid phase. So here first liquid phase we are considering is the raffinate phase, that is water, that is extraction column, raffinate phase, and the second phase is the solvent rich phase, that is 3-methylhexane phase. So we have to select as a key component here in extraction column, that is block parameter. So this will be the first in the bottom phase, and this will be the top phase in solvent rich phase. So we will start the stage pressure atmospheric only, and the temperature also 25 we have mentioned the block parameters. Once that is done, we'll go to the recovery column. We'll run the simulation and we'll keep it like that, and then solvent stream will connect to the red flag column, and there already we'll get the product summary there that will directly enter into the red flag column. So where again we'll define the red flag column parameters, like we started with the number of stages, condenser type we have defined partial vapor, and valid phases is valid vapor, liquid, and distillate and reflux ratio also we have to define it here from initial guess. And then here also the pressure of the column we can mention, temperature also we can mention here, like 25 degrees Celsius the temperature, and pressure 1 bar we have mentioned the condenser pressure. And once the all input parameter is done, then in what results we wanted to be, in what form, temperature profile, pressure profile, or feed composition profile across the column, we can select those checkbox the results to be printed. Like here temperature, liquid and vapor mole flow, liquid or vapor component mole fractions, we want results into these terms. So we can check this box, and we can get our results in this form. Right now I'm leaving the makeup part, because here makeup stream also we can simulate. So right now I'm leaving that part for now, and we are going to now this combination of extraction plus distillation is simulation is done. So now I'm going for the single red flag column, how the condenser duty and those things are there, we will see. So now only I have taken the red flag column, where feed contains acetone and water 50-50%. Acetone is the lighter component we want in top phase, and water is the heavier component in bottom phase. So again here we will define our components first. Components, then model selection is unique RK, and then feed stream feed input data parameters we will enter. And now block parameters we are putting like number of stages, condenser type, reboiler type, and conversions method we have selected like different conversions method are there. This is highly non-ideal mixture is there, so we have selected that. And distillate and reflux ratio we can mention the initial values for the simulation. And condenser pressure is 1, and feed stage we have defined at around 48. So once the column parameter is done, so our target is to get the 99% of acetone in the top phase. So there is an option in Aspen Plus column specification. Inside a specification, there is design specification tab is there. Here, by clicking on that, we can define our design spec, like we want acetone in mass purity of around 99, more than 99%. We can input these parameters like acetone in top phase. Similarly, water in bottom phase, we can define the design spec. Like in bottom phase, we want mass purity of water is more than 99%. So similarly for bottom phase, we can define the design spec. So how many design spec we have defined, that many degree of freedom, as per degree of freedom, we have to give the manipulated variables. So two design spec we have defined. So two manipulated variables like reflux ratio we have to vary inside the column, and distillate rate we have to vary inside the column. So reflux ratio we have taken a lower bound from 0.1 to 20, and distillate rate from 0.1 to 200 kg per hour we have to vary to get that design spec purity. So once we have entered all the details, we will run the simulation and we'll get the results. So results we are getting in terms of heat duty and deboiler duty. Mainly distillation column, these two are the major operating cost involved there. So heat duty in this case we are getting minus 3708.96, and we will compare with the earlier extractor plus distillation heat duty and cooling duty. So earlier
Excuse me, ma'am. Sorry for the interruption. The slides are not moving, ma'am.
Not moving. Oh.
Yes, ma'am.
Now is it visible?
Ma'am, we can see the liquid composition profiles plot. That slide is visible, ma'am.
Still that is going on. Manisha, is it visible now? Manisha?
No, ma'am, the liquid composition plot is visible, ma'am.
Means whatever PDF I have shared that was visible from starting, means like acetone water examples what I was showing. Manisha?
Yes, yes, ma'am.
Ah.
It was visible properly. After this liquid composition profile, it got stuck. You can click on the slide. So,
Yeah, I will try to share one more time. Like liquid composition profile, it was in PPT format, and after that I share one PDF file. That was visible or not? That I have done. Hello?
yes, PDF was not visible.
Okay, so Means, do I need to repeat that again?
Slide is not moving.
Okay. Now is it visible?
Yes, now it's fine. Now it is showing BLE data regression.
Okay, okay. So the PDF file what I have shared, that was not visible earlier. Whatever I spoke regarding the hybrid method, I compared those details, no? So that was not visible. Yeah, now I have shared one PDF. Is it visible? Like the heading is separation of acetone water with.
No, it's not properly visible.
Not properly visible. Okay. Okay, anyway, I will leave that now because I have already explained that. So, means the earlier slide, whatever I shared, I think it was not visible. But my main motto was that through Aspen, we can design different configuration and different kind of process unit operations we can try. And based on that, we can decide that which combination of unit operations or hybrid separation or normal single separation is more efficient to separate those mixtures. So, as I explained earlier, that binary parameters play a very important role in the modeling and simulation part. So, yeah, in many of the simulators, the binary parameters are calculated using the available data bank like Dortmund data bank, like DKMA and those NIST data bank. Through that, we will take the data and we estimate or regress the parameters and we use for our simulation purpose. But in the case where binary parameters are not available, so we have to do the experiments and we have to generate our for like a separation case, like any distillation column separation, we should have the BLE data if the parameters are not available. So in that case, we have to regress those experimental parameters to get the binary parameters, and then finally for the process design and to go for the simulation part. So for that, I am going to show one case study like how to do BLE data regression or LLE data regression if we don't have any binary interaction parameter available in the Aspen Plus. So in that case, like for ethanol and propylene, will show that as a case study. So we first will select our, in this case, we have to go like there are different environment is there in Aspen Plus, properties and simulation environment. So we have to go to the properties environment and we'll select our component ethane and propylene. And then once we have entered our components, we'll go for the appropriate property method selections. So like for polar components and for critical mixtures, we go for equation of state methods. And for light gases, supercritical components, we go for activity coefficient models or activity coefficient models with the Henry's laws. So how we select the regression method? So we'll go to the components. Once we have selected, we have entered the method. Like in this case, for ethane and propylene, we have selected the method Penn-Robinson. Then we'll select these two components for entering the experimental data for the regression. So once we have selected our component, there are two methods to regress the binary parameters. Either if that experimental data is available in Aspen, So we can retrieve those binary data from thermodynamic data bank, or either if it is not available in the thermodynamic data bank, then we have to uh, enter our parameters by selecting this new and VLE data like TXY data. In case of vapor liquid equilibria, we have to enter the temperature, composition in liquid phase, composition in vapor phase to this regression method. And once we have entered our data, we will run the simulation and we'll get our binary interaction parameters. After regression, like this, we will get our regression parameters. So this is a very critical thing in the simulation. So if it is not available, we have to conduct some lab scale trial or pilot scale trial to collect those data, and we first have to regress those parameters, regress those data to get the binary parameters, and then we can go for the simulation environment. And in the VLE regression, maximum likelihood means objective function is generally. Hello.
Yes, ma'am, you're audible, ma'am.
So those BLE data is solved based on the objective function, like there should be minimum error between calculated temperature and experimental, like pressure difference and composition difference in liquid phase and vapor phase. So how we check the reliability of the data by calculating the mean square deviations between experimental and calculated, and by absolute deviations between that. So now I'm going to describe that in form of the case study, like hybrid extraction distillation process for the morphine recovery. Actually, this morphine recovery was a part of downstream process, industrial process, where we were preparing paramethoxy phenyl acetic acid, a component used in the cough syrup. So during the production of PMPA, this morphine water stream generates. So morphine should be recovered from the water stream. So we have to decide the strategy there to separate this morphine. So through Aspen Plus, we have designed a process that is a combination of extraction plus distillation. But here again, if we go through the literature review and everything, we were not having the morphine. Morphine water data was there. Morphine morphine with any other solvent data was not available. So for that initial selection of solvents, we have tried different solvents like toluene, hexane. Based on the criteria, we have selected the different solvents, and with those solvents, we have generated the experimental LLE data in the lab. Then once the LLE data has been generated, we have regressed this parameter in the Aspen Plus, and we got our binary interaction parameters. And then we have gone to the simulation environment where we have optimized the counter current extraction column. And also the vapor liquid equilibria data was not available for the morphine solvent system. So in the lab, we have generated this vapor liquid equilibria data. And once the data has been regressed, we got our optimum binary interaction parameters, and then we go to the simulation environment and optimization of the overall column we get. So for generating the LLE data, we have used means microburette method to generate the tile that we call LLE data or tile line data for the regression. So these data we generated, which we call the Thailand data. So in liquid phase and in the water phase, we have generated this data in the lab. And this data we have entered into the Aspen Plus, and we have regressed the binary interaction parameters. And also before putting this experimental data to the Aspen Plus, first we have to check the consistency of the data. So through using some model like consistency models of LLE or VLE, we have to check the consistency, the data is consistent or not, means is any deviations are there or is any means errors are there. So through consistency, we will reliability of the data will check. So once we have regressed the parameter, like VLE parameters and LLE parameters, we have designed overall process like here in this process, we have considered extraction column, counter current extraction column, followed by heteroisotropic distillation, and finally a recovery column for the solvent recovery. So why we have selected this combination? Because the feed here contains morphine and water. Morphine and water is a highly non-ideal mixture. So using a solvent solvent, uh, separate the morphine into the solvent phase. That is called extract phase, and the remaining will be the raffinate phase. So in extraction column, we don't have to give any extra utility for that. We no need of cooling or we no need of heating purpose here. So we have selected a simple column without any operating parameters. Just the capital cost will be enough here. Then once we are getting our morphine in this extract phase, the water some quantity of water comes into the extract phase. So it forms the heteroisotope. Again, by doing the simple distillation, we have to evaporate all the solvents. So better with what we will do the heteroisotropic distillation, so that water with the solvent will come in the decanter and we can easily separate these two layers, and the remaining morphine and the solvent phase we can take from bottom, and using the simple distillation column, we can recover this to morphine and 2-ethyl-hexanol. So 2-ethyl-hexanol, we can send it for the recovery to the recycling, and we can reuse that. So this is the overall strategy we have set as per our system configuration. And here objective function we have kept as total annual annual cost. Our target is to minimize this TAC. So how we have started the simulation? So feed basis we have taken 10,000 kg per hour as per the industrial client demand. We have set the feed flow basis, and here two process optimization variables we have considered, like continuous and discrete variables we have considered. In continuous variables, S by F ratio we have varies, and in discrete variables the number of stages, feed stages and recycle stages we have varied. And as I said earlier, our objective is to minimize the total annual cost, which is a combination of total capital cost and annual operating cost. So in total capital cost, column cell cost will come, column packing will come, heat exchanger, decanters, or any kind of pump arounds will come into the total capital cost. And in annual operating cost, steam cost will come, and cooling water cost will cover there. So in our simulation, as I said, we have started with the selection of solvent, and we have generated the Thailand data. Using the Thailand data, we have entered into the Aspen regression, Aspen properties environment for the regression of the LLE and BLE data. And we have regressed the binary interaction parameters. And once we got our parameters, we have run the hybrid simulation. So once S by F ratio variation, we are seeing the extract in extract phase how much we are getting our morphine recovery. Once we are getting the maximum morphine recovery in the top phase by S by F variation and number of stages variation in the extraction column, we are targeting the morphine recovery in the extract phase. Once our target is achieved, we will go to the next stage. Next stage is the extract phase. We are sending it to heteroisotropic distillation column that contains some amount of water, total morphine and total solvent will be there. So our target is to remove some amount of water from that. So water and that solvent makes a heteroisotrope, so that we are trying to remove in the heteroisotropic distillation column. So Their variables are like feed stages, recycle stages, and total stages we have to vary till the time all the water comes into the top phase. So once the target is achieved, we will go to the the recovery column. In recovery column, we are trying to separate the morphine and the solvents. So top product purity morphine we have considered, or either we can set like in bottom phase morphine should be uh, less than 0.1%, or water in bottom phase should be less than 1%. Like that, we have set it the variable, and once the target is achieved, we will see the minimum TSC and optimized result we'll get. This strategy is we have followed for the simulation and optimization, that is equation linear optimization. These are the results of the process simulation where we have regressed these Thailand data, and we got very less deviations between experimental and simulated. And these are the parameters we got from that, which we have used in the simulation. And LLE column, we got the S by F versus recovery versus TAC. So at 5.8 around, we are getting 5.8 around, we are getting minimum TSC with the optimum recovery. And similarly for the heteroisotropic distillation column, we got a stage, the minimum stage at around 13, and we got the maximum recovery of water in that column. And similarly for the D2 column, at 7 stage, we are getting all the morphine in the top phase. So this is the overall breakup of the TAC, like capital cost, reboiler cost, condenser cost, and utility cost like steam cost and cooling water cost. This is the overall breakup which we got through simulation. And this is the optimized result across each unit operation which we have simulated. Like whatever feed compositions we are giving, and what we got is the optimized like number of trays, temperature and pressure condition. What is the output stream composition is there, like in extract phase water is 0.092 mole fraction, morphine composition, and overall solvent is there, and in raffinate phase mostly water is the major composition there. So this extract phase, we took it into heteroisotropic distillation where we have removed almost all the water, and in the bottom phase mostly morphine and ethyl acetate, 2-ethyl-hexanol is there. That again we are sending it for the recovery. So in the top phase we are getting almost more than 99% purity of morphine, and in the bottom phase the morphine is less than means ppm level. It means it is in ppm level. So based on the simulation, what we got in 10,000 kg per hour, we have scaled down that parameter. We have done the experiments in the laboratory scale, where height of the column we have maintained, the ratio we have maintained what we got from the simulation. So the ratio of height of the column we maintain 53.5 centimeters is the dia of column, and inlet temperature we maintain 30, height of packing we have maintained, and feed flow rate 1 means S by F ratio 0.87, what we got the optimum. At that S by F ratio we have operated this column, and we got around morphine recovery in the extract phase 99.8% from prediction in simulation, and in lab we are getting around 98%, means deviation of 1.8% we are getting, and time of extraction we got around 4 hours, and water loss we are getting around 9%. This is the overall laboratory setup where we are feeding a feed mixture from top of the column, and solvent from here from bottom of the column. So extract phase we are withdrawing just above the packing, some equilibrium zone we are leaving it out, and we are extracting extract phase we are collecting from here, and from bottom we are getting the rapid phase collection. So this is overall. So the main advantage of doing the process simulation in design, because it minimizes the experimental, like as earlier example I said, we have done the simulation in Aspen Plus, and at the optimum condition we have run the lab scale experimentation. So it minimizes the experimental and scale up effort, and also we should not always blindly trust the simulation tool, because how we are putting the input parameters, the process performance based on that. So we should always be sure, we should have always the solid understanding of the systems to input the parameters to any kinds of simulation softwares. So, thank you. And now any queries there, then
Thank you so much, ma'am, for enlightening us with very valuable information. Now with that, we will go ahead and take some time for questions. I request the participants to raise their hands regarding any question, or you can post your queries in the chat box also. Ma'am, there's a question. Which type controller is used in distillation column control?
yeah, Mansa, can you repeat the question?
Which type controller is used in distillation column control?
Actually, here we have done the steady stator, but generally in plant and all, we use PLC SCADA system. I don't have that much control regarding that knowledge, but PLC like programming generally will be there. And in this, what I said in red flag column means the simulation is based on mesh equation it solves. Like there will be mass and energy balance will be there, and across the column, it will solve the liquid composition and vapor composition. Summation should be 1, and it should be in equilibrium. Like that, it solves the mesh equations there.
Ma'am, there's another question. Where did you procure SCADA system? Is it National Instruments?
Yeah, through any software company, whatever instrument we buy from the vendor, like distillation column we procure, they only provide that is SCADA system. Means if our requirement is there from there we will get. Not especially with any software company we tie up for the procurement. Means like we need any total system and we want a SCADA with that, so we will ask with that equipment company only to provide the SCADA system. So they will contact with the relevant company and they will procure and they will give us. So we generally do not means contact directly to the SCADA company, means software company for procurement.
Hello, ma'am.
Yeah.
Hello.
Yes, I can hear.
Am I audible to you, ma'am?
Yeah, you are audible, sir. You are
Hello.
audible, sir. You are
Am I
audible,
audible to
sir.
you, ma'am?
Yes, you are audible, sir.
Yeah, ma'am. Basically, I'm Dr. Ajit Lavre from
Yes.
Vicky Patil Engineering College, Ahmednagar, Maharashtra.
Okay.
You have given you a very nice lecture regarding as far as process optimization it is concerned over there. But one question I want to ask you, whether this Aspin Plus, it is the open source software or we have to buy that software, ma'am?
No. Actually, this is not an open source. For academic license, it is somewhat less cost, but for industrial license, it demands more. So it's not an open access software.
And ma'am, basically, I'm related to the process control and instrumentation system.
Yeah, I
Like
got to know that most of the faculty have registered from computer science. background, so I don't know how much you people got from my lectures. Means I tried more to the overview of that, not going into the much details about the means chemicals and those. So
Ma'am, basically, what is just I will take your few minutes and because later on I will discuss with you, no doubt here. But
yes,
what I did that modeling and optimization of level control system or temperature control system.
control system.
Yeah. So in that, what I did, the input output data I have collected, then optimization for the optimization of that process, J algorithm and artificial bee colony optimization I have used, no doubt here. But for more complex system, like say suppose dryer, heat exchangers, and your distillation column system, because our college it doesn't have any that software. But still, I'm having a strong wish and desire to do the more research in this process control system. So just I read from your PPT. You are from CSIR, IICT Hyderabad.
Hyderabad, yes.
Hello.
Yes, I can hear you.
Uh, so, ma'am, just I want to ask you, can we do the experimentation at CSIR, IICT Hyderabad, ma'am, through your reference?
Regarding that, I need to talk to the management. Yes, this type of arrangements is there in IICT, but with that institute, initial MOU will be signed, and then collaborative kind of research can be done. So initially, between the institution, one MOU should be signed.
Yeah, but if I am single person and if I am having strong wish and desire to do the research in the process control system,
Okay.
so can I approach you because my sister is staying in Hyderabad?
Okay.
And that's what I'm asking you.
Okay, basically, I'm not from process control background, but even though if you want to conduct any kind of research here, so I'll talk to my HOD, means this type of person is there, they want to continue some kind of research. So I have to talk to my HOD and I have to take the permission, then maybe it can be done. Yeah.
Ma'am, can you give your mobile number, please?
Yeah, I will drop here the mail ID or. So you can mail me on that mail ID, no? So I'll give the information there.
Yeah, ma'am. Sure.
I'll share my mail ID here in chat box.
Okay, ma'am. Thank you.
So I have in chat box, I have sent my mail ID. You can mail me there, then we can discuss more there. Manisha, I think
Any more questions from the participant? I think no questions.
Okay, ma'am.
Okay, thank you, Manisha. Thank
I
you,
think
everyone here. Thank you.
on this note, we will end today's session. Tomorrow at 9 a.m., there will be a session on the topic predicting right feed mix to control the product quality based on predictive analytics by Mr. Ravi Kiran, Senior Process Engineer, Grace Division, Chemical India Private Limited, Chennai. We look forward to meet you all tomorrow. Thank you.